Hello there and welcome to Science for Sleep, the place where we can wander through some of the stranger corners of science without needing to hurry through any of them. Tonight, we're going to look far beyond the planets, beyond the stars, beyond the familiar shape of the Milky Way, and into a question that reaches almost as far as astronomy allows us to see. There is something unusual about the way certain groups of galaxies appear to move. Galaxies are never completely still. Our own Milky Way is moving, nearby galaxies are moving. Entire clusters containing hundreds or thousands of galaxies travel through space under the influence of gravity. None of that is surprising. Gravity has been pushing and pulling matter around since the early universe, and after more than 13 billion years, the result is a cosmos filled with motion. But astronomers once reported something much harder to explain. They found evidence suggesting that enormous collections of galaxy clusters, separated by extraordinary distances, might share a common motion through space, instead of drifting in random directions according to the gravitational attractions we can see around them. These clusters appear to be participating in a much larger flow, a cosmic current. The researchers gave it a name that sounds almost designed for a late-night science video: dark flow. And no, despite the name, it is not the universe wearing a black cape and behaving suspiciously. The word dark was used because whatever might be responsible for this proposed motion could not easily be identified in observations. If the signal were real, the visible distribution of matter in the region did not seem sufficient to account for it. There appeared to be motion without an obvious nearby source, powerful enough to produce it. That led to a remarkable possibility. Perhaps whatever was influencing those galaxies was so distant that we could not see it. Perhaps it was beyond the part of the universe that is observable to us. That is the idea we're going to examine tonight, not as a confirmed discovery, because it is not one. Dark flow remains controversial. Some measurements have supported the idea of an unusual large-scale motion, while other analyses, including later observations from the Planck satellite, did not find evidence for the enormous bulk flow originally claimed. So we are dealing with a scientific mystery in the proper sense of the phrase, an observation that was reported, debated, tested again, challenged, and still raises useful questions about how much of the universe we can actually know. That uncertainty is part of what makes the subject interesting. Science does not always give us a neat answer, followed by a satisfying little tick in a box. Sometimes it gives us an unusual result and then spends years arguing politely, and occasionally not so politely, about whether the unusual result was real in the first place. Dark flow belongs firmly in that category. Before we go any farther though, where are you listening from tonight? Maybe you're somewhere surrounded by city lights, where only a few bright stars make it through the glow. Maybe you are somewhere darker, where the Milky Way can actually be seen stretching overhead. Perhaps it is late at night for you, or perhaps you have decided that a discussion about galaxies being pulled toward something outside the observable universe is perfectly reasonable afternoon listening. There are worse ways to spend an afternoon, and wherever you happen to be, consider something simple for a moment. You are sitting on Earth. Earth is rotating. Earth is also orbiting the Sun. The Sun is moving around the centre of the Milky Way. The Milky Way itself is travelling through space. Our galaxy belongs to a local collection of galaxies, and that collection is also moving relative to more distant structures. Even while you're lying completely still, perhaps with a pillow arranged exactly the way you like it, you are participating in several different motions at once. Fortunately, none of them require you to hold onto the mattress. Motion is normal in the universe. The difficult part is explaining why things are moving in the directions and at the speeds that they are. Gravity provides most of the answer. If you place matter in space, matter attracts other matter. Stars gather into galaxies. Galaxies gather into groups and clusters. Clusters form larger structures. Over enormous spans of time, regions containing slightly more matter than average pull additional material toward themselves. The universe, viewed on the larger scales, resembles a vast network. There are dense regions filled with galaxies. There are long filaments connecting them. Between those structures are enormous voids containing much less matter. Astronomers sometimes call this arrangement the cosmic web. If you could somehow step far outside it and look down at the distribution of galaxies from an impossible distance, you would not see an even scattering of little points. You would see structure, and where there is structure, there is gravity. A galaxy near a massive concentration of matter will be pulled toward it. A cluster of galaxies near an even greater concentration will respond as well. These motions are sometimes called peculiar velocities, which sounds slightly judgmental, but simply means motion, in addition to the general expansion of the universe. The universe is expanding overall. On sufficiently large scales, distant galaxies tend to move away from one another as space expands. This is the broad pattern described by the Hubble expansion. But gravity adds local complications. Imagine putting a collection of raisins into rising bread dough. As the dough expands, the raisins move farther apart. That gives you the general expansion. Now imagine that the raisins could also attract one another gravitationally. The analogy becomes less useful for baking, but more useful for cosmology. Some raisins would move slightly toward nearby concentrations, even while the dough continued to expand. Galaxies do something broadly similar. Astronomers can therefore ask two separate questions. How fast should a galaxy be moving because of cosmic expansion, and how much additional motion does it have because of nearby gravity? That second motion can tell us something important. It can reveal mass, even mass that is difficult to see directly. For decades, astronomers have used the motions of galaxies to trace gravitational structures in the universe. One famous example is the region known as the Great Attractor, a concentration of mass toward which our own galaxy and many neighbouring galaxies have a measurable motion. The name sounds like a contestant on an intergalactic talent show, but it refers to a real gravitational feature associated with large concentrations of galaxies. Later surveys revealed that the situation was more complicated than a single object pulling everything toward it. The Great Attractor lies within a much larger landscape of galaxy clusters and superclusters, including the enormous Shapley concentration farther away. So when astronomers see coordinated motion, their first thought is not usually, "Something outside the universe must be pulling us." Their first thought is much less dramatic. What mass have we missed? Maybe there are galaxies hidden behind the Milky Way. Maybe the distribution of dark matter has not been mapped correctly. Maybe a distant supercluster contributes more gravitational influence than expected. Maybe the measurements themselves contain an error. Astronomers are very good at producing exciting possibilities, but they're also professionally trained to spend a great deal of time asking whether the exciting possibility could simply be a troublesome instrument. Dark flow became interesting because the reported motion appeared to extend across a scale much larger than the familiar local flows. The original work was led by Alexander Kashlinsky and collaborators, who examined hundreds of galaxy clusters using measurements connected to the cosmic microwave background. The cosmic microwave background, which we will explore properly in a little while, is ancient radiation left over from the early universe. It fills space in every direction and gives astronomers something extraordinarily useful. A kind of reference background against which the motion of galaxy clusters can be studied. A galaxy cluster contains not only galaxies, but huge quantities of extremely hot gas. Photons from the cosmic microwave background can pass through that gas and interact with electrons inside the cluster. Depending on the circumstances, those interactions can leave tiny signatures in the microwave background. One of those signatures is known as the kinetic Sunyaev-Zeldovich effect. There is absolutely no requirement that you remember that name. If you're already half asleep and kinetic Sunyaev-Zeldovich effect has entered your dreams as the name of an eccentric railway conductor, that is perfectly acceptable. The important idea is much simpler. The effect can provide information about the motion of galaxy clusters relative to the background radiation. Kashlinsky's team looked for a collective signal across large numbers of clusters. They reported evidence of a coherent motion extending across immense distances, eventually arguing that the pattern reached more than 2.5 billion light-years in scale. NASA described the claimed motion as roughly 1,000,000 miles per hour along an axis associated with the direction of the constellations Centaurus and Hydra, although even the exact direction of the flow had uncertainties. Just consider the scale involved. 2.5 billion light-years. Light itself, travelling at about 300,000 kilometres every second, would require 2.5 billion years to cross that distance. When the first ancestors of our genus were appearing on Earth, a beam of light beginning a journey across a region that large would still have had almost its entire trip ahead of it. Our species appeared. Civilizations rose. People invented agriculture, writing, wheels, clocks, telescopes, electricity, television, and eventually the extraordinary human achievement of arguing with strangers through comment sections. That light would still be travelling. When we discuss motion on scales like these, ordinary intuition becomes almost useless. Yet the reported patterns seem to suggest that clusters spread across this enormous region shared a preferred direction of motion. That is what made researchers pay attention. A small local flow can be explained by local gravity. A much larger coherent flow is harder. Under the standard cosmological picture, matter began with small variations in density. Gravity amplified those variations over time, producing the galaxies, clusters, filaments, and voids we observe today. Large-scale motions naturally appear in this process. But the larger the region you examine, the more those different gravitational pulls should tend to average out. One cluster may fall toward one concentration, another cluster somewhere else may fall in another direction. Zoom out far enough, and the universe should become statistically homogeneous, meaning that no direction or location is fundamentally special on very large scales. Dark flow, if it existed with the originally proposed strength and scale, seemed uncomfortable within that expectation. Where was everything going? More importantly, why? That was when the discussion moved from unusual astronomy into unusual cosmology. Suppose you map all the matter you can see in a very large region. You include galaxies, you account for clusters, you estimate dark matter, you calculate the gravitational attractions, and the observed motion still seems too large. There are only so many places left to look. One possibility would be that our model of the motion is wrong. Another would be that the data contains some effect that has not been properly removed. But there is a more exotic possibility. The gravitational influence could come from matter beyond our observable horizon. The phrase, observable universe, is important here. It does not necessarily mean the entire universe. It means the region from which light, or some other causal signal, has had enough time to reach us during cosmic history. The universe has a finite age. Light has a finite speed. Space has also been expanding while that light travels. Together, those facts create a limit to what we can observe. There are regions so distant that their light has not reached us. Depending on the true size and geometry of the cosmos, there could be vastly more universe outside our observable region. Possibly much more. Perhaps infinitely more. We do not currently know. This means that when we look at the farthest objects our telescopes can detect, we are not necessarily looking at a physical wall. There is no known shell at the edge with a sign saying "Universe ends here." Thank you for visiting. We are looking toward a horizon. The distinction matters. Stand on a beach and look toward Earth's horizon. You can only see so far, but you would not conclude that the ocean stops at the line where the water disappears from view. More ocean exists beyond what you can see. Cosmology is more complicated than a beach, naturally, because cosmologists have equations and beaches have ice cream, but the basic lesson is useful. A horizon is a limit on observation, not necessarily a limit on existence. So if dark flow were real, one possible explanation proposed by its advocates was that extraordinarily large structures might exist beyond our cosmic horizon. Those unseen structures could have influenced matter in our region of the universe, particularly in the extremely early cosmos, leaving behind a preferred motion that still survives today. This is where the popular description usually becomes something outside the universe is pulling galaxies toward it. It is a wonderful headline. It is also slightly misleading. If such a structure existed, it would not necessarily be outside the universe. It could be outside the observable universe. That is a very different claim. The first would suggest something beyond all of physical reality as we understand it. The second merely suggests that physical reality extends farther than the region we can currently see, which most cosmological models already allow. Still extraordinary, but for a different reason. We would be detecting the influence of something we could not directly observe. It would be a little like sitting in a closed room with no windows and noticing that every hanging object tilts slightly toward the same wall. You cannot see what is on the other side, but the consistent pull would make you curious. Perhaps there is something massive beyond it, or perhaps the floor is tilted, or perhaps your measuring equipment is wrong. That last possibility is important because dark flow has never enjoyed universal acceptance. When better data became available from the European Space Agency's Planck mission, scientists searched for bulk motions of galaxy clusters using the microwave background with improved observations. They did not detect the enormous large-scale flow that the earlier dark flow interpretation would lead one to expect. A Planck analysis reported no significant bulk flow detection in the cluster samples it examined and placed an upper limit of about 254 km per second for a blind bulk flow search, finding results consistent with the standard cosmological model. That did not cause every researcher involved with dark flow to abandon the subject. Scientific disagreements rarely disappear that neatly. Different teams have argued about filtering methods, cluster selection, calibration, statistical treatment, and how effectively the kinetic Sunyaev-Zeldovich signal can be separated from other effects in the microwave sky. Measuring these motions is extremely difficult. We are not watching individual galaxy clusters slide across the sky like cars passing a window. Their apparent movement is much too subtle for that. Researchers are trying to extract tiny statistical signals from a background filled with other signals. The cosmic microwave background has its own temperature variations. Galaxy clusters contain hot gas that produces additional microwave effects. Radio sources can interfere. Dust can interfere. Instrument noise can interfere. Even the way you process a map can matter. It is one of those areas where the sentence, "We measured something strange," is usually followed by several years of people asking, "Yes, but exactly how did you measure it?" That is not science failing. That is science functioning normally. An extraordinary claim has to survive attempts to make it disappear. If better instruments, different analyses, and independent teams repeatedly recover the same effect, confidence grows. If they do not, the mystery shifts. Instead of asking what caused the phenomenon, researchers begin asking what caused the measurement. Both questions can teach us something. That leaves us in an interesting position tonight. Dark flow may not be a hidden cosmic river carrying vast portions of the universe toward an unseen mass. There is currently no scientific consensus that the originally claimed flow exists at the reported strength. But the possibility opened a door onto several much larger questions that are completely real. How do astronomers know how galaxies move? What is the largest gravitational structure in our cosmic neighbourhood? Where does the Great Attractor fit into all of this? How far can gravity influence matter? What exactly is the observable universe? What might lie beyond its horizon? Could events from before the familiar stage of cosmic inflation leave traces that are still detectable today? And perhaps the strangest question of all, could we ever learn anything about a region of the cosmos that light from our own era can never reach? Those questions remain interesting whether dark flow survives or not. There is another reason the subject is worth spending some time with. Human beings are accustomed to thinking of the sky as a collection of objects. There is the moon, there is Mars, there is a star, there is a galaxy, there is another galaxy. Astronomy gradually teaches us to replace that picture with something more connected. Objects in the universe are not simply sitting beside one another. They interact, they orbit, they collide, they fall into clusters. Clusters respond to larger gravitational environments. Matter traces filaments stretching across hundreds of millions of light years. Empty regions can influence the overall motion too, not by pulling, but because there is less gravitational attraction coming from those directions than from denser ones. Our own galaxy participates in this motion. The Milky Way does not occupy a quiet seat while the rest of the cosmos performs around it. We are part of the same gravitational landscape. Measurements of the cosmic microwave background reveal that the solar system, and the local group along with it, moves relative to that ancient radiation. Part of understanding large-scale flows is therefore understanding our own motion. It is strangely easy to forget this. You may feel stationary now. The room is not moving relative to you. The bed is hopefully staying where it was placed. The glass of water on the bedside table is displaying no obvious relativistic behaviour. At human scales, still is a perfectly useful word. Cosmically, it is almost meaningless without specifying what you are still relative to. Earth rotates relative to the Sun. Earth orbits relative to the Sun. The Sun orbits within the Milky Way. The Milky Way moves relative to nearby galaxies. The local group moves relative to the cosmic microwave background. Every answer creates another reference point. And somewhere inside those layers of motion is the question that produced dark flow. Can the movements we see be explained entirely by the matter inside the region we can observe? For most measurements, the standard picture works remarkably well. That should not be overlooked. Modern cosmology is not a collection of guesses held together by hopeful expressions. The standard model successfully explains an enormous range of observations, from the broad structure of the cosmic microwave background to the statistical distribution of galaxies and the expansion history of the universe. That success is precisely why a genuine large-scale anomaly would matter so much. If galaxy clusters really were flowing together across billions of light-years at a speed far beyond normal expectations, cosmologists could not simply shrug and add it to a list. Something in the picture would need attention, perhaps unseen structure, perhaps unusual conditions in the early universe, perhaps physics that has not yet been incorporated into the standard model, or perhaps, much less dramatically, a measurement technique producing a signal that looks more convincing than it really is. Science has room for all of those possibilities until evidence begins closing doors. And that is where our route through this subject really begins. Not with something beyond the universe definitely pulling galaxies toward it. Not with a mysterious object waiting just outside the cosmic horizon. And certainly not with an enormous invisible hand dragging clusters through space, although that would save us several pages of mathematics. We begin with motion, a very particular kind of motion. Before anyone could argue about what might exist beyond the observable universe, astronomers first had to notice that galaxies and clusters do not simply follow the smooth expansion of space. They have additional velocities produced by the uneven distribution of matter around them. Those movements form currents through the cosmic web. Some are well understood, some have taken decades to map, and some have led astronomers toward concentrations of matter so large that even the name Great Attractor begins to sound surprisingly restrained. To understand why dark flow caused such excitement, we need to know what an ordinary cosmic flow looks like first, how gravity creates it, how astronomers measure it from hundreds of millions of light-years away, and at what point an ordinary gravitational drift begins to look unusually large. That takes us away from the hypothetical edge of the observable universe for a little while, and back toward the galaxies themselves, where the first clues are hidden in the difference between the motion expected from cosmic expansion and the motion astronomers actually measure. That difference between expected motion and measured motion is where the story becomes much more interesting, because the universe is not expanding like a perfectly smooth balloon, with every galaxy obediently remaining in its assigned position. Gravity constantly interferes. Galaxies pull on other galaxies. Groups pull on nearby groups. Huge concentrations of matter tug on entire clusters, and empty regions can affect motion as well, simply because there is less matter pulling from those directions. The result is that the expansion of the universe has currents running through it. Not currents made of water, of course, and not streams that have a clearly marked beginning and end. These are large-scale patterns in the velocities of galaxies. Astronomers call them bulk flows when many objects across a region share a common component of motion. To understand what that means, imagine looking down at a river from high above. The river itself moves downstream, but individual leaves on its surface do not all follow exactly the same path. One gets caught in a small whirlpool, another drifts toward the bank, a third is pushed sideways by a branch. They are all participating in the overall flow of the river, while also having smaller motions caused by their immediate surroundings. Galaxies behave in a roughly comparable way. The overall expansion of space provides one motion. Gravity produces additional motion on top of it. Cosmologists call that additional movement a peculiar velocity. The word peculiar does not mean that a galaxy is doing something embarrassing. It simply means the velocity that remains after astronomers subtract the motion expected from the expansion of the universe. That sounds straightforward until you remember that a galaxy may be hundreds of millions of light years away. You cannot attach a speedometer to it. You cannot place a police officer beside a galaxy cluster with a radar gun and ask it to slow down. Astronomers have to infer these motions from light. One of the most useful tools is redshift. When light from a galaxy reaches us, its wavelength can be stretched. In an expanding universe, more distant galaxies generally show greater cosmological redshift because the space through which their light has travelled has expanded. If astronomers know how far away an object is, they can estimate how quickly it ought to be receding according to cosmic expansion. Then they compare that expected recession with what the spectrum actually shows. The difference can reveal the object's peculiar velocity along our line of sight. Suppose cosmic expansion predicts that a particular galaxy should be moving away from us at 6,000 kilometers per second, but its observed redshift corresponds to something slightly different. Part of that difference may come from gravity. Perhaps the galaxy is falling toward a nearby cluster. Perhaps the cluster itself is moving toward a larger concentration of matter. Repeat this process for many galaxies across the sky, and a larger pattern can begin to emerge. This is where individual motions become cosmic geography. A single galaxy moving unexpectedly does not tell you very much. Several thousand galaxies moving in related ways can reveal where matter is concentrated, including matter that is difficult to see. Our own cosmic neighbourhood offers a good example. The Milky Way is not simply moving with the expansion of the universe. It belongs to a small collection of galaxies called the Local Group. That group includes Andromeda, the Triangulum Galaxy, and dozens of smaller galaxies. The Milky Way and Andromeda are actually approaching one another, rather than being carried apart by cosmic expansion. Their mutual gravity dominates at this distance. The Local Group itself also has a larger motion relative to the cosmic microwave background. That motion is important because the cosmic microwave background gives astronomers something close to a universal reference frame for large-scale cosmology. The microwave background is not equally warm in every direction from our point of view. One side of the sky appears slightly hotter and the opposite side slightly colder. Most of that large dipole pattern is interpreted as the result of our motion. We are moving toward the hotter direction and away from the colder one. It is the cosmic equivalent of noticing that rain hits the front windshield of a moving car more strongly than the rear window. Except instead of rain, we are measuring radiation released when the universe was only about 380,000 years old, which makes the morning commute seem rather less impressive. Our motion relative to this background is several hundred kilometers per second. That creates an obvious question. What is causing it? The answer is not a single nearby object. For a while, astronomers focused heavily on a region that became known as the Great Attractor. The Great Attractor is not one enormous galaxy, or a mysterious object hiding behind a curtain. It is a region associated with a significant concentration of mass in our larger cosmic neighbourhood. Part of the difficulty in studying it came from its position in the sky. It lies in roughly the same direction as the thick plane of the Milky Way. That is inconvenient. Our galaxy contains enormous amounts of dust, gas and stars, and when astronomers try to look through the plane of the Milky Way toward distant galaxies, much of the view is obscured. This part of the sky has long been called the zone of avoidance, another wonderfully dramatic astronomical name for what is essentially the universe saying, there are too many stars in the way. Infrared observations, radio surveys, X-ray studies and other techniques eventually allowed astronomers to see more of the structures hidden behind our galaxy. What emerged was not a simple picture of one giant concentration pulling the local group toward it. There were clusters and superclusters spread across a much larger region. One especially important concentration lies even farther away, in the direction of the Shapley supercluster. Shapley contains a remarkable concentration of galaxies and galaxy clusters. Its gravitational influence appears to contribute to the motion of our local region. At the same time, nearby cosmic voids also matter. This can initially sound strange. How can emptiness push anything? It does not. A void does not contain some mysterious anti-gravity substance. Instead, imagine that you are standing between two groups of people, pulling on ropes attached to you. If the group on your left suddenly becomes much smaller, you will move toward the right. The right-hand group has not become stronger. There is simply less pull from the other side. Something similar can happen on cosmic scales. A region with less matter contributes less gravitational attraction than surrounding dense regions. The combined effect can help produce a net motion away from the void and toward denser parts of the cosmic web. So even our own movement through the universe is created by a complicated gravitational landscape. Nearby structures matter, distant structures matter, underdense regions matter, dark matter matters, and astronomers have to reconstruct all of this from observations that cover enormous distances. This is why large-scale flows are not inherently mysterious. The standard cosmological model predicts them. Matter was not distributed perfectly evenly in the early universe. There were small density differences. Some regions contained a little more matter than others. Gravity gradually amplified those differences. Over billions of years, slightly denser regions drew in more material. Galaxies formed, clusters formed, filaments formed. Voids emptied further as matter migrated toward denser surroundings. The motions we observe today are partly the accumulated result of that long gravitational process. If a galaxy finds itself near a massive concentration, it falls toward it. If many galaxies occupy the same large region, they may share part of that motion. There is nothing unusual about that. The interesting part begins when the shared motion becomes very large. The farther apart the galaxies are, the less likely they are to be responding to exactly the same local structure. Think again about the river. If leaves separated by a few meters drift in the same direction, that is ordinary. They are in the same current. If leaves separated by hundreds of kilometers somehow showed an additional shared motion that could not be explained by the river, wind, geography, or anything else you could identify, you would probably start checking your measurements. That is close to the problem dark flow introduced. In 2008, Alexander Kashlinsky and colleagues reported evidence that hundreds of distant galaxy clusters shared a coherent motion. The team used observations from NASA's Wilkinson Microwave Anisotropy Probe, usually called WMAP. WMAP had been designed primarily to map the cosmic microwave background, the faint afterglow from the early universe. Its measurements were extraordinarily useful for cosmology, but Kashlinsky's group attempted to use them for a different purpose as well. They wanted to study the motion of galaxy clusters. Galaxy clusters are excellent targets because they are enormous. A large cluster may contain hundreds or thousands of galaxies. More importantly for this measurement, the space between those galaxies is filled with very hot gas. That gas can reach temperatures of tens of millions of degrees. At those temperatures, electrons move freely through the cluster. Photons from the cosmic microwave background pass through this hot material on their journey across the universe. Occasionally, a microwave photon interacts with one of those electrons. That interaction changes what astronomers observe. There are two related effects that matter here. The first is the thermal Sunyaev-Zeldovich effect. Hot electrons in a cluster can transfer energy to cosmic microwave background photons. This produces a characteristic change in the microwave signal seen toward the cluster. Astronomers have used the thermal effect extensively to detect and study galaxy clusters. The second is the kinetic Sunyaev-Zeldovich effect. That one is much more relevant to dark flow. If the cluster itself is moving relative to the microwave background, the scattered radiation receives a tiny Doppler shift. A cluster moving toward us leaves a slightly different temperature signal from a cluster moving away from us. In principle, that gives astronomers a way to measure peculiar velocities without relying entirely on traditional galaxy distance methods. In practice, the signal is extremely small. NASA's description of the original work noted that the kinetic effect was less than 1/10 as strong as the related thermal Sunyaev-Zeldovich effect, and was difficult to detect for individual clusters. Kashlinsky's team therefore relied on large samples of X-ray selected clusters and searched statistically for a common signal. This is an important detail because dark flow was never a case of scientists pointing a telescope at one galaxy cluster and watching it race across space. They were extracting a weak signal from many objects. The technique depended on finding the microwave temperature pattern at the positions of known clusters, reducing stronger signals, averaging over the sample, and looking for a dipole that might indicate collective motion. A dipole simply means that the signal has one direction on one side and an opposite direction on the other. If many clusters are moving together relative to the microwave background, their combined kinetic Sunyaev-Zeldovich signatures should create such a pattern. The team's first analysis used several hundred galaxy clusters. They reported a bulk motion approaching 1,000 kilometers per second. NASA described the motion in the early results as nearly 2 million miles per hour directed toward a patch of sky between the constellations Centaurus and Vela. Later work expanded the cluster sample and extended the claimed signal to greater distances. By 2010, the researchers reported that the pattern persisted to distances of roughly 2.5 billion light-years. The direction was described somewhat differently in the later analysis, with the flow axis roughly centered towards Centaurus and Hydra, and the team emphasized that there was uncertainty about which way along that axis the clusters were actually moving. That uncertainty matters. If you hear that hundreds of galaxy clusters are moving towards something, it creates a very specific mental image. A hidden object sits somewhere ahead. Everything is falling toward it. That was not exactly what the observations established. The original measurements were better described as evidence for motion along a preferred axis. Determining whether the clusters were moving in one direction along that axis or the opposite direction was more difficult. Even so, the scale of the claimed flow was the real surprise. Ordinary gravitational flow should weaken as the volume being studied grows. On smaller scales, matter is lumpy. You have galaxies here, clusters there, voids somewhere else. The gravitational field is uneven. As you examine progressively larger volumes, however, those irregularities should increasingly average out. One direction may contain a large cluster, but another contains another structure. The farther you zoom out, the closer the universe should approach the large-scale statistical uniformity assumed in modern cosmology. This principle is called homogeneity. It does not mean the universe looks identical everywhere on small scales. Clearly it does not. A star is different from empty intergalactic space. The center of a galaxy cluster is different from the middle of a void. Homogeneity means that when you average matter over sufficiently enormous scales, one large region should not be fundamentally different from another. There is a related principle called isotropy. That means there should be no special direction in the universe when viewed on sufficiently large scales. North is not cosmologically privileged, neither is south. There should not be one preferred direction toward which enormous portions of the observable cosmos are moving for no local reason. The standard model does allow some residual bulk flow. The key questions are how fast it should be and how far it should extend. Small flows are expected. Larger flows become progressively less probable. A coherent flow of the magnitude originally associated with dark flow, extending across billions of light years, would be very difficult to produce using only the gravitational influence of structures mapped within the observable region. That is why the result attracted so much attention. If the measurement was correct, astronomers had two broad categories of explanation. Either something important about large-scale structure had been missed, or the assumptions behind the standard cosmological picture needed another look. Yet there was also a third possibility, and it was much less exciting but scientifically unavoidable. The signal might not represent a real cosmic flow at all. It might arise from the method. This is where dark flow became controversial very quickly. Detecting the kinetic Sunyaev-Zeldovich effect across a large population of clusters is difficult because the microwave sky contains many other signals. The primordial cosmic microwave background itself has temperature variations. The thermal Sunyaev-Zeldovich effect is stronger than the kinetic one. Clusters vary in mass, temperature, and gas distribution. Radio emission can contaminate measurements. Infrared sources can contribute. Instrumental noise is present. Galactic foreground emission must be dealt with. Then researchers have to decide how to filter the microwave maps. Different filters can change which parts of the signal survive. The size of the aperture used around each cluster can matter. The cluster catalogue matters. Calibration matters. Converting a measured microwave dipole into a physical velocity introduces additional assumptions. This does not make the technique useless. It simply means that an unexpected signal has to survive a large number of tests before astronomers can confidently interpret it as the motion of matter. Kashlinsky and collaborators argued repeatedly that the signal remained when they expanded their samples and used additional WMAP data. In their later work, they stated that they had traced the proposed flow to much greater distances than in the original analysis. Their interpretation was that the gravitational field responsible could not be produced entirely by the distribution of matter visible within the surveyed region. They suggested that the source might be associated with structure outside the observable horizon. That suggestion is what transformed an obscure velocity measurement into one of the more provocative cosmological claims of the period, because now the question was not merely whether a set of clusters was moving. The question was whether we might be seeing evidence from somewhere we cannot directly observe. Before accepting that idea, however, other teams had to reproduce the measurement, and that did not happen cleanly. Some studies using different techniques found large bulk motions on various scales, while others found results compatible with the standard cosmological model. Then the Planck satellite provided much more detailed microwave observations. Planck was launched in 2009 and mapped the cosmic microwave background across multiple frequencies with greater sensitivity and resolution than WMAP in many relevant areas. That gave astronomers another opportunity to search for peculiar velocities through the kinetic Sunyaev-Zeldovich effect. A 2013 Planck analysis examined X-ray selected galaxy clusters and searched for bulk motion. The researchers did not find a statistically significant large-scale bulk flow in their sample. Their blind search placed a 95% confidence upper limit of 254 km per second on the bulk flow amplitude, and they concluded that the measurements were consistent with the standard lambda-CDM cosmological model on very large scales. That result was a serious problem for the original dark flow interpretation. If hundreds of clusters were really sharing a coherent motion approaching roughly 1,000 km per second over enormous distances, a more sensitive microwave survey ought to have had something important to say about it. Planck did. It said that it did not see compelling evidence for such a flow. The disagreement did not instantly settle every technical issue. Kashlinsky's group continued to argue that differences in methodology, filtering, calibration, and cluster treatment affected the comparison. This sort of debate is common when researchers are working near the edge of what instruments can measure. It can become technical very quickly. One group may say that a filter removes noise efficiently. Another may argue that it also removes part of the signal. One analysis may convert a temperature dipole into velocity using one calibration. Another may question whether that conversion adequately represents the cluster population. From outside the field, it can look as though everyone is staring at the same sky and somehow seeing different universes. In reality, they're often trying to determine whether a signal far smaller than several unwanted signals survives a complicated chain of analysis. That is difficult work. It is also the reason replication matters. There is an additional complication. The phrase bulk flow covers more than the specific dark flow claim. Astronomers have measured large-scale peculiar velocities using supernovae, galaxy distances, redshift surveys, and other methods. Different surveys probe different regions and different depths. Some have reported motions somewhat larger than the simplest theoretical expectations. Others have found close agreement with lambda CDM. These results should not automatically be grouped together and called evidence for dark flow. A bulk flow extending a few 100 million light-years can arise from ordinary large-scale structure. The original dark flow claim was unusual because of the combination of its proposed speed and extraordinary spatial extent. That distinction tends to disappear in popular retellings. A headline may say that scientists have found galaxies moving strangely. Then another study measures a modest local bulk flow. Soon the two are treated as confirmation of the same mystery. They are not necessarily the same phenomenon. Cosmology is particularly vulnerable to this because every distance sounds enormous. A structure 100 million light-years across sounds impossibly huge from a human perspective. Yet cosmologically, it may still be relatively local. A flow measured over 150 million light-years and a flow supposedly extending over several billion light-years are very different claims. The scale changes the physics. Gravity from known structures can plausibly organize motion across one range. Push the same coherent velocity across a much larger fraction of the observable universe, and the explanation becomes more difficult. That is the important point to carry forward. There really are cosmic currents. Galaxies really do have peculiar velocities. The local group really is moving relative to the cosmic microwave background. Large concentrations such as the Great Attractor region and the Shapley concentration really do influence the gravitational motion of galaxies in our neighbourhood. Those facts are not controversial. Dark flow takes the idea and asks whether a similar common motion persists far beyond the scales where known structures should dominate. The original measurements said yes. Later Planck results gave a strong reason to doubt that conclusion. And somewhere between those two results sits the question that made the subject famous. What would it mean if a genuine coherent motion remained after every visible gravitational source had been accounted for? To answer that properly, we have to understand the background against which the clusters were being measured in the first place. The cosmic microwave background may look like a faint, almost uniform wash of radiation, but it is one of the most information-rich things astronomers have ever observed. It tells us about the universe before stars existed. Its tiny temperature differences reveal the seeds from which later galaxies grew. Its dipole exposes our own motion, and when its photons pass through the hot gas of galaxy clusters, they can carry a subtle record of how those clusters are moving. That ancient light is the reason anyone could search for dark flow at all, and understanding what it actually measures will make the disagreement over the claimed signal much easier to follow. The dark flow story did not begin with someone searching for something beyond the observable universe. There was no telescope pointed toward the edge of space with a research proposal that said, "Let us see whether something enormous is pulling galaxies from somewhere we cannot see." The discovery came from a much more ordinary scientific goal. Researchers were trying to measure how galaxy clusters move, using a very faint effect hidden inside measurements of the cosmic microwave background. That distinction is important because unexpected discoveries are often more convincing when the strange result was not the thing researchers originally went looking for. If you design an experiment specifically to find a particular phenomenon, you have to be especially careful that your analysis is not quietly helping you find what you hope to see. In this case, the technique itself had been developed years earlier as a way to extract information about the velocities of galaxy clusters. Alexander Kashlinsky, an astrophysicist at NASA's Goddard Space Flight Center, had been working with Fernando Atrio Barandella of the University of Salamanca on the problem since around 2000. Their basic difficulty was easy to describe and unpleasant to solve. Galaxy clusters move. The movement should leave a measurable imprint on the cosmic microwave background. Unfortunately, that imprint is tiny. A large galaxy cluster contains enormous quantities of hot gas. The gas is not sitting quietly between the galaxies. It is heated to millions of degrees, with free electrons moving through the cluster at high speeds. Meanwhile, photons from the cosmic microwave background are passing through the universe from every direction. Some of those photons travel through galaxy clusters. When they encounter the hot electrons inside a cluster, they can scatter. That scattering slightly changes the microwave radiation we observe. The general family of effects involved is named after the physicists Rashid Sunyaev and Yakov Zeldovich. One version, the thermal Sunyaev-Zeldovich effect, comes from the random thermal motion of the hot electrons. Because those electrons are extremely energetic, they can transfer some of their energy to microwave photons. That effect is relatively strong and has been used for decades to study galaxy clusters. The version Kashlinsky and his colleagues needed was much weaker. It is called the kinetic, or kinematic Sunyaev-Zeldovich effect. Instead of mainly telling us about the temperature of the cluster gas, this effect contains information about the motion of the entire cluster relative to the cosmic microwave background. If a cluster is moving toward us, the microwave photons scattered by its gas receive one kind of tiny shift. If the cluster is moving away from us, they receive the opposite kind. In principle, you can use that difference to estimate how the cluster is moving. In principle is doing a great deal of work in that sentence. The kinetic effect is extremely faint. NASA described it during the original dark flow announcement as less than 1/10 as strong as the thermal effect, and at the time it had not been cleanly measured for an individual cluster. Trying to determine the velocity of one distant cluster this way was rather like trying to hear someone whispering from the back of a crowded railway station while several people closer to you were discussing their holiday plans. The whisper may be there. That does not mean you can easily separate it from everything else. Kashlinsky and Atrio Barandella realized that there was another approach. Instead of depending on one cluster, use many of them. Noise tends to behave differently from a genuine shared signal. Random contributions may point in different directions and partially cancel when many measurements are combined. If hundreds of galaxy clusters share some common motion, however, that component should remain. The idea had been developed years before the phrase dark flow entered astronomy. Then researchers needed a sufficiently large sample of clusters. That required another group of astronomers, including Harold Ebeling and Dale Kuchevsky, who assembled a catalogue of X-ray bright galaxy clusters spread across much of the sky. X-ray observations were particularly useful because the same hot intracluster gas responsible for the Sunyaev-Zeldovich effects also glows strongly in X-rays. A bright X-ray cluster therefore gives astronomers a useful sign that there is a substantial amount of hot gas available to scatter microwave photons. The catalogue eventually contained close to 700 clusters for the first major analysis. Some were relatively nearby by cosmological standards, others were billions of light years away. Getting those distances was not a casual process. Each cluster had to be identified, observed, characterized, and assigned a redshift. Harold Ebeling later noted that measuring a distance for one cluster could require about an hour of telescope time, on top of the years spent finding the systems in the first place. 700 clusters therefore represented quite a lot of patient astronomy. The next ingredient came from WMAP. The Wilkinson Microwave Anisotropy probe had been launched by NASA in 2001. Its main purpose was not to study dark flow. WMAP was built to map tiny differences in the temperature of the cosmic microwave background across the entire sky. Those differences contain information about the early universe, including its age, composition, geometry, and the initial density fluctuations from which later cosmic structure developed. For Kashlinski's team, the WMAP maps offered something else. They contained microwave measurements at the exact locations where the galaxy clusters sat. The researchers could take the catalogue of cluster positions and examine the WMAP temperature data at those points. But looking directly at the raw map would not be enough. The primordial microwave background itself contains fluctuations. There are foreground signals, there is instrumental noise, there is the stronger thermal Sunyaev-Zeldovich contribution. The kinetic signal they wanted was buried underneath all of this. Their method therefore involved filtering the microwave maps. The aim was to suppress as much of the unwanted cosmic microwave background signal as possible, while preserving the component that could be associated with moving clusters. Then they examined the microwave temperatures at the cluster locations. One quantity they looked for was a dipole. A dipole is simply a directional pattern. Imagine painting a sphere so that one side is slightly warmer and the opposite side slightly cooler. That is a dipole. If a population of galaxy clusters has a common velocity relative to the cosmic microwave background, the kinetic Sunyaev-Zeldovich effect should generate a directional pattern of that kind at the cluster positions. The researchers were not asking whether every cluster had exactly the same velocity. That would be unrealistic. Each cluster has its own local gravitational environment. Instead, they were asking whether the sample contained an overall common component of motion. This is a little like watching several hundred people walking through a busy railway station. Everyone is moving differently. Some are going to platforms, some are heading toward exits, some are standing directly in the worst possible place while checking their phones. But if the entire crowd is also being carried slowly to one side by a moving floor, you might be able to detect that common motion statistically, even though every individual person is doing something different. In 2008, the team applied their technique to the 3-year WMAP data, together with the catalogue of roughly 700 X-ray selected clusters. They reported a statistically significant dipole at the cluster locations. The papers describing the measurement appeared that year, with Kashlinski, Atrio Barandella, Kashevsky, and Eberling arguing that the signal was consistent with a coherent large-scale bulk flow. The size of the inferred motion was what immediately made the result unusual. The researchers estimated a bulk velocity approaching 1,000 kilometers per second. That is several million kilometers per hour. NASA summarized the early result as nearly 2 million miles per hour. More surprising than the speed was the apparent consistency of the direction. The clusters seemed to show motion toward a roughly 20-degree wide region of the sky, between the constellations Centaurus and Vela, and the signal did not appear to disappear as the researchers looked at more distant clusters. The initial analysis suggested that the motion continued to distances of at least around 1 billion light-years. That immediately raised a problem. Cosmologists already expected bulk flows. Nothing about galaxies moving together was new. The issue was that large-scale coherent motion should generally become smaller when you average over larger and larger regions. A cluster can be pulled strongly toward a nearby concentration of matter. A group of clusters can share a motion caused by a supercluster. But once your sample covers an enormous volume of the universe, many different gravitational attractions should begin to cancel statistically. A massive region pulls one way, another concentration pulls somewhere else. Voids reduce attraction from other directions. The larger the region becomes, the less likely it should be that everything retains a strong common velocity in one preferred direction. Kashlinski's team believed their observed motion was too large to fit comfortably into that expectation. They also checked whether known matter in the region could explain it. There was no obvious concentration large enough to produce the proposed flow across the distances involved. The great attractor was not sufficient. The Shapley concentration did not neatly solve it either. Known large-scale structures could certainly contribute to local peculiar velocities, including our own, but the reported signal appeared to extend much farther. This was where the interpretation became unusual. If the gravitational source could not be found inside the region being observed, perhaps the source lay farther away. Possibly, much farther away. Kashlinski used the term dark flow to describe the motion. The name deliberately echoed dark matter and dark energy. Dark matter is called dark because we do not observe it directly through emitted light, although we see its gravitational effects. Dark energy is the name given to whatever is responsible for the accelerated expansion of the universe. Dark flow followed the same naming habit. There appeared, according to the team's interpretation, to be a large motion whose cause could not be identified. Naturally, astronomy had now collected enough dark things that the universe was beginning to sound as though someone had forgotten to pay the electricity bill. The name was memorable, which helped the result attract attention. The interpretation attracted even more. One possibility suggested by Kashlinski and colleagues involved conditions existing before or during the earlier stages associated with cosmic inflation. Inflation is the idea that the very young universe passed through an extremely rapid period of expansion. A tiny region could have expanded enormously in a fraction of a second. This helps explain several otherwise puzzling features of the universe, including why distant regions have such similar properties. But inflation also introduces an interesting issue. The universe we can currently observe may represent only a small portion of a much larger whole. Regions now far beyond our observable horizon could have existed in causal relationships with our region at very early times, depending on the detailed model. If enormous density variations existed beyond the part of the universe we can see, their early gravitational influence might have left a kind of directional imprint on the matter that eventually became our observable cosmos. This did not mean that some object was currently reaching across an impossible boundary and pulling galaxies like a magnet. The popular description of something beyond the universe pulling us makes the situation sound much simpler than the proposed physics. The idea was closer to this: a very large-scale gravitational gradient, potentially associated with structure beyond our present horizon, might have influenced the initial motion of matter in our observable region. That primordial motion could then survive as a bulk velocity. It would be a fossil of conditions on scales larger than we can see directly. That possibility was extraordinary. It was also speculative. At this stage, the researchers still had a more immediate job. They had to determine whether the signal persisted when better data and larger cluster samples became available. WMAP continued observing the microwave sky. Meanwhile, the galaxy cluster catalogue grew. The team returned to the problem using 5 years of WMAP measurements, and a sample expanded to more than 1,000 X-ray clusters. The larger catalogue allowed them to divide the clusters into distance ranges. This mattered because a real large-scale flow should show some degree of consistency across those ranges. Suppose you find a directional signal in relatively nearby clusters. That could come from a regional gravitational feature. Now look twice as far away. If the signal disappears, you may simply have mapped a local flow. If it remains, the scale of whatever is producing it must be larger. The researchers divided their cluster sample into several distance slices and measured the dipole independently in them. According to their analysis, the preferred axis remained similar. The exact ellipses representing the inferred direction changed with distance, because the measurements contained uncertainty. But the overall alignment persisted. Their updated result extended the claimed flow to roughly 800 megaparsecs, or around 2.5 billion light-years. The speed in the later description was around 1 million miles per hour. The axis was roughly associated with the southern constellations Centaurus and Hydra. There was an interesting complication. The data were better at identifying an axis than determining which direction along that axis the clusters were travelling. Imagine drawing a straight line through the sky. You can say with reasonable confidence that the motion seems aligned with that line. But a line has two directions. Are the clusters moving one way or the opposite way? The later data favoured motion outward along the Centaurus-Hydra direction, but the team acknowledged that they could not firmly exclude the reverse direction. That detail is easy to lose once the result is translated into headlines. Galaxy clusters show a statistical dipole consistent with motion, along an uncertain axis is scientifically more careful. It is not a particularly tempting headline. Something outside the universe is pulling galaxies toward it tends to receive a little more attention. The 2010 analysis also gave the researchers an opportunity to test possible errors more closely. They checked how the signal changed with the X-ray luminosity of the clusters. This was useful because more X-ray luminous clusters generally contain denser hot gas and should produce a stronger Sunyaev-Zeldovich signal. If the measured dipole genuinely came from interactions between microwave photons and cluster gas, stronger clusters should contribute more strongly. The team reported that this correlation was present. They argued that this behavior made ordinary instrumental noise or unrelated primordial microwave fluctuations less likely explanations for the dipole. Their expanded analysis, based on more than 1,000 clusters, described a roughly constant bulk velocity extending to very large distances. From the team's perspective, this was encouraging. They had found an unexpected signal in the 3-year WMAP data. They increased the dataset. They increased the number of clusters. They pushed the measurement farther into the universe, and the signal, in their analysis, remained. Kashlinsky summarized the experience in a sentence that captured the situation rather well. This was not something they had set out to find, but they could not make it disappear. That is the sort of sentence scientists enjoy saying only after spending a considerable amount of time trying to make something disappear. Because trying to destroy your own result is part of the job. Change the filter, separate the clusters into different groups, look at different distances, test stronger and weaker clusters, simulate random skies, examine possible foreground contamination, ask whether the telescope itself could introduce the pattern. If the result vanishes after one reasonable change in the analysis, you have learned something useful. If it keeps returning, curiosity grows. The Darkflow team believed they had reached that second situation. Other researchers were not convinced. Some questioned the statistical significance. Others questioned the filtering technique. There were concerns about how accurately the temperature dipole could be converted into an actual cluster velocity. Another issue was whether residual cosmic microwave background fluctuations could create apparent patterns in the cluster sample. The fact that the kinetic Sunyaev-Zeldovich signal was so weak meant that relatively small methodological differences could matter. This is where the story stopped being a simple discovery and became a scientific argument. That argument is essential, but it is worth appreciating how strange the original result seemed before moving into the disagreement. Hundreds of galaxy clusters had been selected because they were bright in X-rays. Their positions were compared with an all-sky microwave map made for a completely different scientific purpose. At those positions, after filtering the microwave background, researchers reported a directional temperature pattern. They interpreted that pattern as a shared velocity. Then they expanded the sample, increased the observational data, pushed farther outward, and reported that the same broad axis remained visible. If that interpretation had been unquestionably correct, it would have implied that a huge region of the cosmos possessed a common motion that the known distribution of matter could not easily explain. And once you reach that point, the next question is unavoidable. What exactly were those clusters being measured against? They were not being compared with a stationary grid painted onto space. There is no such grid. The reference was radiation, very old radiation. It had been travelling through the universe since long before there were galaxies, planets, stars like the sun, or anyone staying awake late enough to wonder why hundreds of clusters might be moving in the same direction. That radiation is the cosmic microwave background, and to understand why a tiny temperature shift in it could be interpreted as the motion of a galaxy cluster billions of light years away, we need to look much more closely at where this background came from, what its strange mottled pattern tells us, and why astronomers sometimes describe it as the oldest detailed picture of the universe we will ever be able to see. The radiation used to measure those distant cluster motions is not ordinary starlight, and it did not come from galaxies. It was already travelling through space long before the first galaxy existed. In fact, the cosmic microwave background comes from a period when the universe was so young that there were no stars, no planets, no black holes formed from dead stars, and certainly no galaxy clusters available to participate in mysterious large-scale flows. The universe was only about 380,000 years old when this light began travelling freely. Today the universe is about 13.8 billion years old, so the cosmic microwave background gives us a view of reality at an extraordinarily early stage. This is why it is often described as the oldest light we can observe. Calling it a photograph is not quite correct, but the comparison is useful. When astronomers create an all-sky map of the cosmic microwave background, they're effectively looking at a very early snapshot of the universe. Instead of showing stars and galaxies, the map shows tiny differences in temperature across the sky. Those differences preserve information about variations in density that existed when the cosmos was still extremely young. The galaxies surrounding us today grew, indirectly, from those tiny variations. To understand how that happened, it helps to imagine what the universe was like before the cosmic microwave background was released. The early universe was hot, very hot. Matter did not exist in the familiar arrangement we see around us now. There were no neutral hydrogen atoms calmly drifting around. Temperatures were high enough that electrons could not remain bound to atomic nuclei for long. Instead, the universe contained a dense plasma of free electrons and nuclei mixed with radiation. Light existed, but it could not travel very far. Photons constantly encountered free electrons and scattered from them. Imagine trying to use a bright torch in extremely thick fog. The light leaves the torch, but it immediately scatters from tiny droplets in the air. You cannot see very far because the photons do not travel directly from distant objects to your eyes. The young universe behaved in a related way. It was filled with a kind of cosmic fog. Light was everywhere, but the universe was opaque. As cosmic expansion continued, the universe cooled. Eventually, the temperature dropped enough for electrons to remain attached to nuclei, producing electrically neutral atoms, mostly hydrogen and helium. Cosmologists call this period recombination, although the name is slightly confusing because the electrons and nuclei were not necessarily being reunited after some earlier long-term relationship. Physics kept the name anyway. Once enough free electrons disappeared into neutral atoms, photons could travel much greater distances without constantly scattering. The cosmic fog cleared. Light that had previously been trapped within the plasma could now move freely through space. Those photons have been travelling ever since. We detect them today as the cosmic microwave background. There is an important difference between what those photons were when they began their journey and what we detect now. When they were released, the universe was thousands of degrees hotter than it is today. As space expanded, the wavelengths of the photons stretched along with it. Shorter wavelength radiation gradually became longer, wavelength radiation. After billions of years of expansion, the ancient light has been stretched into the microwave part of the electromagnetic spectrum. Its present average temperature is about 2.7 Kelvin, only a few degrees above absolute zero. ESA's Planck observations measured a background that matches this very cold microwave glow while preserving tiny temperature differences across the sky. If human eyes could see microwave wavelengths, the night sky would therefore look very different. You would still have the nearby microwave emission produced by our own galaxy and other sources, but after those were properly separated, you would discover that the entire sky contains ancient radiation. It does not come mainly from one direction. It surrounds us. Look north, and it is there. Look south, and it is there. Look toward a region with many galaxies, and it is there. Look toward a region that appears almost empty, and it is there too. This does not mean Earth sits at the center of a spherical shell left over from the Big Bang. Any observer located in another distant galaxy would also see a cosmic microwave background surrounding them. The reason is that the Big Bang was not an explosion from one location into pre-existing empty space. Cosmic expansion happened throughout space. the material that eventually became our observable universe, was once much hotter and denser everywhere. The microwave background is therefore not a distant wall around us. It is light arriving from matter that was once much closer to our own location before billions of years of expansion separated the regions. This is one of those ideas that becomes less comfortable the longer you picture it, which is fairly normal in cosmology. The existence of such leftover radiation had been predicted before anyone successfully measured it. Researchers, including Ralph Alpha, Robert Herman, and George Gamow, had worked on the consequences of a hot early universe in the 1940s. A universe that began in a hot, dense state should leave behind radiation that cooled as the universe expanded. Then, in the 1960s, two radio astronomers named Arno Penzias and Robert Wilson encountered something irritating. They were working with a large radio antenna at Bell Laboratories in New Jersey. Their instrument contained an unexplained background noise. It appeared regardless of where they pointed the antenna. This was a problem because when an instrument produces unwanted noise, the first assumption is not usually that you have discovered radiation from the early universe. The first assumption is that something is wrong with the instrument. Penzias and Wilson investigated possible causes. They checked the equipment. They considered radio interference. They examined environmental sources. Famously, pigeons had been living in part of the antenna and had left behind material that was considerably less scientifically valuable than cosmic background radiation. The antenna was cleaned. The unwanted microwave signal remained. The noise did not behave like a local source. It seemed to come from every direction. At roughly the same time, a group at Princeton University led by Robert Dick was preparing to search for exactly the kind of background radiation predicted by hot Big Bang cosmology. When the two groups learned of one another's work, the significance of the Bell Lab signal became clear. Penzias and Wilson had detected the cosmic microwave background. The discovery was reported in 1965, and Penzias and Wilson later received part of the 1978 Nobel Prize in Physics for it. At first, knowing that the radiation existed was already a major result. It strongly supported the idea that the universe had once been much hotter and denser. But astronomers soon wanted to know whether the microwave background was perfectly smooth. If the early universe had been completely uniform, with matter distributed identically everywhere, there would have been a serious problem. The universe we see today is not uniform on ordinary scales. Matter is concentrated. There are stars. There are galaxies. There are clusters. There are enormous filaments containing many galaxies. There are huge voids with far less matter. All of that structure had to begin somewhere. Gravity can amplify small differences. Give one region slightly more matter than another, and it produces slightly stronger gravity. It attracts additional matter. The region becomes denser. Its gravitational attraction increases further. Over enough time, very small early differences can develop into enormous cosmic structures. But gravity needs something to begin with. The early universe, therefore, had to contain tiny variations in density. Finding evidence of those variations became one of the great goals of observational cosmology. NASA's Cosmic Background Explorer satellite, better known as COBE, supplied a crucial result. COBE was launched in 1989. Among its achievements, it measured the spectrum of the cosmic microwave background with extraordinary precision and found it to be extremely close to the thermal spectrum expected from a hot early universe. Then its differential microwave radiometer detected tiny intrinsic variations in the microwave background across the sky. The variations were only about 1 part in 100,000. That means the early universe was astonishingly smooth, but not completely smooth. Those faint differences were enough. They represented the early density variations that gravity could later amplify into the cosmic structures surrounding us today. If you have ever seen a map of the cosmic microwave background, these variations are usually represented using different colours. There may be red areas, orange areas, blue areas, and darker patches. It can look extremely dramatic. The actual temperature differences are not dramatic at all. The colours are exaggerated so that humans can see the pattern. Without that visual enhancement, the microwave background would appear remarkably uniform. The mottled pattern is extremely subtle. One region was slightly denser, another was slightly less dense. There were variations in the temperature and gravitational conditions of the plasma. Those variations created the pattern recorded in the radiation. Then billions of years passed. Gravity went to work. The slightly denser regions attracted matter. Dark matter helped provide gravitational wells into which ordinary matter could fall. Gas collected, stars formed, galaxies assembled, galaxies merged, clusters grew. The modern cosmic web emerged from beginnings that were surprisingly modest. You could therefore look at the CMB map as a very early plan of the structures that would later appear, not a detailed street map with a convenient label saying, "Milky Way will eventually be built here." The relationship is statistical and physical rather than that direct. Still, the information contained in the microwave background allows cosmologists to determine remarkable things about the universe. They can study its geometry, they can estimate the amount of ordinary matter, they can constrain the amount of dark matter, they can investigate the history of cosmic expansion, they can study the initial fluctuations from which large-scale structure developed. With sufficiently precise measurements, a faint microwave glow becomes a record of the conditions that shaped nearly everything we see around us. WMAP greatly improved that record. Launched in 2001, the Wilkinson Microwave Anisotropy Probe produced detailed all-sky measurements of the cosmic microwave background. It observed for years and provided increasingly precise maps of the temperature variations. These measurements helped establish the modern standard cosmological model and improved estimates of the universe's age and composition. Later came ESA's Planck spacecraft. Planck mapped the microwave sky at still greater precision and across a broad range of frequencies. Its final map showed the temperature anisotropies of the cosmic microwave background in extraordinary detail. The familiar Planck image contains a complicated pattern of warmer and cooler regions, representing density variations when the universe was only around 380,000 years old. These increasingly precise maps might sound somewhat removed from our story about galaxy clusters moving through the modern universe. They are not. The cosmic microwave background provides something astronomers badly need when talking about large-scale motion. It provides a reference. Motion is always relative to something. If you say that a car is travelling at 60 km per hour, you normally mean relative to the road. If two cars travel beside each other at exactly the same speed, each driver can look sideways and see the other car apparently sitting still. Neither car is truly stationary relative to the road. They are simply stationary relative to each other. Galaxies create the same problem on a much larger scale. There is no obvious solid cosmic road beneath them. Space itself is expanding. Everything is moving. So what does it mean to say that the Milky Way has a particular velocity through the universe? One useful answer is to compare our motion with the cosmic microwave background. The CMB has a distinctive large-scale pattern produced by our own velocity. One side of the microwave sky appears slightly hotter than average. The opposite side appears slightly colder. This is known as the CMB dipole. The basic reason is the Doppler effect. When we move toward the incoming microwave radiation from one direction, the radiation appears slightly blue-shifted and therefore hotter. Radiation arriving from the opposite direction appears slightly red-shifted and colder because we are moving away from it. The effect is much larger than the tiny primordial fluctuations cosmologists usually want to study. Before analysing the subtle early universe pattern, researchers therefore removed the dipole associated with our motion. COBE measurements clearly showed this smooth hot-to-cold pattern, and NASA describes it as arising from the motion of the solar system relative to the distant cosmic background. This gives us a practical cosmic rest frame. An observer moving so that the CMB dipole disappears would be at rest with respect to the average cosmic microwave background. That does not create an absolute state of rest in the old Newtonian sense. Relativity still works perfectly well. But for cosmology, it gives us an extremely useful reference frame associated with the large-scale expansion of the universe. Our solar system is not at rest in that frame, neither is the Milky Way, neither is the local group. We are moving. That fact immediately connects the CMB with peculiar velocities. If a galaxy cluster is also moving relative to the microwave background, photons passing through the hot gas in that cluster can carry a small imprint of the cluster's motion. This is the kinetic Sunyaev-Zeldovich effect that the dark flow researchers attempted to measure. The CMB acts as the background illumination. The cluster acts as a moving cloud of electrons. The scattered photons carry information about the motion. It sounds elegant when described this way. The difficulty is that the CMB itself is not perfectly uniform. Those tiny primordial temperature differences are exactly what made COBE, WMAP, and Planck so scientifically valuable. But when you're trying to detect an even smaller effect from moving galaxy clusters, the same variations become unwanted background. Suppose you examine the microwave temperature toward one particular cluster. The value you measure might be influenced by several things. Part of it may be primordial CMB anisotropy. Part may come from the thermal Sunyaev-Zeldovich effect. Part may come from the kinetic effect. Part may come from radio emission. Part may come from dusty galaxies. Part may come from our own Milky Way. Part may simply be instrumental noise. Now separate all of those accurately enough to determine the cluster's velocity. It becomes clear why researchers preferred a statistical approach involving hundreds of clusters. The dark flow team filtered WMAP maps to reduce the primordial microwave fluctuations, and then examined the remaining signal at known cluster locations. Because the clusters had been selected using X-ray observations, the researchers knew they contained hot gas capable of interacting with CMB photons. They then searched for a common dipole across the cluster population. If the clusters were moving randomly, much of their kinetic signal should average away. If they shared a coherent velocity, a directional pattern might remain. That is the measurement that produced the proposed dark flow signal. But the cosmic microwave background adds another layer to the puzzle. Its own large-scale properties are remarkably uniform. This is one of the foundations of modern cosmology. After correcting for our local motion and foreground contamination, the CMB temperature is almost the same in every direction. The small anisotropies follow statistical patterns that are broadly consistent with a universe that is homogeneous and isotropic on very large scales. There are some large-angle anomalies in CMB maps that cosmologists have debated for years, but the broad picture remains extremely successful. That creates tension with a very large coherent flow. If the universe becomes statistically uniform on large scales, then giant peculiar velocities should become increasingly unlikely as the scale grows. Consider again the original density fluctuations. Some regions were slightly overdense, others were slightly underdense. These produced gravitational attractions in different directions. On smaller scales, those differences generate substantial motions. A galaxy can fall toward a cluster. A cluster can move toward a supercluster. Our own local region can respond to the combined influence of dense structures and voids. But as you average over larger volumes, there should be less leftover directional imbalance. One side will contain a concentration of matter. Another side will contain something else. The net velocity should generally decrease. The CMB allows cosmologists to predict statistically how much large-scale motion should result from the pattern of primordial density fluctuations. This does not mean they predict the exact speed of every individual galaxy. They predict the distribution of likely motions across different scales. A bulk flow of a few hundred kilometers per second over a certain region may be perfectly reasonable. A substantially faster coherent flow, extending across billions of light years, becomes much harder to accommodate. This is where the dark flow result became more than a technical curiosity. The same ancient radiation used to establish the standard cosmological picture was being used to claim evidence for a motion that seemed difficult to explain within that picture. The CMB was serving as both the map and the measuring background. The seeds visible in its tiny temperature variations should eventually produce the structures and velocities seen today. If modern clusters were moving much faster and much more coherently than those seeds could reasonably produce, something appeared to be missing. Perhaps the measurement was wrong. That possibility always had to remain open. Perhaps known structures had been underestimated. Perhaps the statistical interpretation needed a revision. Or perhaps the observable region itself did not contain everything responsible for the motion. That last idea becomes easier to understand once we distinguish two very different horizons. The cosmic microwave background marks what is sometimes called the surface of last scattering. It is the farthest electromagnetic light we can observe directly in the ordinary sense because, before recombination, the universe was opaque to photons. We cannot simply build a larger optical telescope and look through that opaque plasma. More powerful equipment does not make fog transparent when the fog itself prevents information from travelling freely. There may be other ways of learning about earlier times, including gravitational waves or indirect signatures, but ordinary light reaches a natural limit at the CMB. The observable universe, however, extends conceptually beyond the distance represented by the CMB because of cosmic expansion and the history of how signals have travelled, and the entire universe may extend vastly farther still. The CMB therefore gives us our oldest detailed electromagnetic map, but not necessarily a map of everything that exists. There could be regions outside our observable horizon. If inflation occurred, the larger universe may be unimaginably greater than the portion visible to us. Under ordinary circumstances, that sounds scientifically frustrating, but not immediately relevant. If something is beyond the observable horizon, we cannot simply point a telescope at it. Dark flow introduced a much more provocative possibility. What if something beyond the region we can observe had left an imprint on the motion inside it? Not necessarily a gravitational pull acting across the horizon right now, but a large-scale influence established in the early universe, before expansion separated regions so dramatically. Then the coherent motion of galaxy clusters could act as indirect evidence of conditions beyond our visible cosmic domain. That is why the size of the claim flow mattered so much more than its memorable name. A nearby gravitational current tells us about nearby matter. A flow across hundreds of millions of light years may tell us about enormous structures, but a strong common motion persisting across billions of light years would demand a source or initial condition on an even larger scale. And when Kashlinski's team tried to compare the reported motion with the gravitational landscape represented by known galaxies, clusters, and the standard pattern of early density fluctuations, they argued that the numbers did not fit comfortably. The clusters appeared, in their analysis, to be moving too coherently across too large a region. That was the point at which the search for a velocity became a search for a cause. The obvious suspects were the great concentrations of matter already known to astronomers. The Great Attractor had been associated with unusual motions in our local cosmic neighbourhood for decades. Beyond it lay even larger concentrations such as the Shapley supercluster. Dark matter added gravitational mass that could not be mapped simply by counting visible stars. Huge structures could hide partially behind the plane of the Milky Way. Before invoking anything beyond the observable universe, all of those possibilities had to be considered. But there was a basic gravitational problem. The farther the reported flow extended, the larger and more distant its source would need to be if ordinary attraction were responsible. At some point, a local explanation starts requiring so much mass spread across such an enormous scale that the proposed solution becomes nearly as surprising as the mystery itself. And that is where the next piece of the problem begins: how large a gravitational influence would actually be necessary to move such an enormous collection of galaxy clusters together, and whether anything inside the universe we can map could plausibly provide it. If the proposed motion really did extend across billions of light years, then the problem was no longer simply that galaxy clusters were moving. The problem was that the usual gravitational suspects did not seem large enough to explain the motion being reported. Gravity is very good at creating currents in the universe. Put enough mass in one place and nearby matter begins to fall toward it. Spread that mass across clusters and superclusters, and the effect can extend for hundreds of millions of light years. This is not unusual. It is one of the main reasons galaxies do not follow the smooth expansion of the universe perfectly. But gravity has a price. If you want to produce a larger velocity, you generally need more mass, more time, a smaller distance, or some combination of all three. That sounds obvious, but it becomes surprisingly useful when astronomers try to explain large-scale motion. A galaxy cluster moving a little faster than expected may be responding to an ordinary nearby concentration of matter. A vast collection of clusters sharing a strong common motion across an enormous region demands something more substantial. The original dark flow measurements therefore forced a very practical question. What could be massive enough to do this? Astronomers already knew about several extraordinary concentrations of matter in roughly the relevant part of the sky. The most famous was the Great Attractor. The Great Attractor had entered astronomy long before dark flow. Researchers studying the velocities of nearby galaxies found that the local group, which includes the Milky Way and Andromeda, was not moving exactly as a simple picture of cosmic expansion would suggest. There was a substantial peculiar motion toward the general region of Hydra and Centaurus. Something in that direction appeared to be influencing us gravitationally. At first, identifying the source was difficult because the thick plane of the Milky Way blocks much of the view. Stars, dust and gas in our own galaxy obscure distant structures lying behind them. Astronomers call this difficult band of sky the zone of avoidance, which sounds like a place where a sensible spacecraft would refuse to stop for fuel. The hidden region was gradually explored using wavelengths that can penetrate the obscuring material more effectively than ordinary visible light. One important structure found there is the Norma cluster, also known as Abell 3627. It is a rich cluster of galaxies located in the general Great Attractor region. For a time, it was tempting to imagine that the Great Attractor problem had a simple answer. There was a large hidden concentration of mass, galaxies were falling toward it, and the mystery had been solved. The real universe was less cooperative. As surveys improved, astronomers discovered that the motion of our local region could not be reduced neatly to one giant object. There are multiple concentrations of matter spread across a much larger volume, and the gravitational field depends on all of them. Farther away lies the Shapley concentration, one of the richest concentrations of galaxies in the nearby universe. Shapley is enormous. It contains many galaxy clusters grouped within a dense region, hundreds of millions of light years away. Because it lies in roughly the same broad part of the sky as the Great Attractor, astronomers naturally asked whether Shapley might be supplying some of the missing gravitational pull. It does contribute to large-scale motions, but even that answer becomes complicated. Studies of the local velocity field have found that the motion of the local group is built from the influence of many structures rather than a single dominant attractor. A 2026 reconstruction of the nearby universe, for example, concluded that no single structure, including the traditional Great Attractor, should be expected to account for the entire velocity of the local group. The inferred convergence of large-scale flows also changes depending on the scale being examined, shifting from the Virgo region on smaller scales toward Hydra Centaurus and Shapley on larger ones. That is a useful reminder before returning to dark flow. When astronomers say something is moving toward an attractor, they're often simplifying a gravitational landscape that contains clusters, superclusters, filaments, voids, and large amounts of dark matter. Gravity does not care what name humans give the region. It responds to the entire distribution of mass. Imagine standing in a room with dozens of people pulling you gently with strings from different directions. One person might be stronger, another might be closer. A group in one corner might collectively pull harder than any individual. Remove several people behind you, and the imbalance changes again. Your motion would be the result of the whole arrangement, not necessarily the nearest person with the most dramatic name. The cosmic version is similar, except the strings are gravity, the people are structures containing trillions of stars, and the room is inconveniently large. This is why astronomers map galaxies across as much of the sky as possible. Visible galaxies act as traces of matter. They do not reveal everything, because dark matter supplies most of the matter in the universe, but the locations of galaxies and clusters help researchers reconstruct where gravitational concentrations are likely to be. They can then calculate the peculiar velocities those concentrations should produce. For nearby flows, this works reasonably well. The local group's motion relative to the cosmic microwave background can be linked to the uneven distribution of matter around us over large distances. The exact contributions of particular structures remain an active subject of research, but the basic mechanism is ordinary gravitational instability. Dark flow was different because the proposed motion did not appear to stop when the sample moved beyond the familiar local structures. Kashlinski's team reported that the common flow persisted through several distance ranges and reached roughly 2.5 billion light-years. NASA's description of the result emphasized that the team believed the distribution of matter in the observed universe could not account for the claimed motion. At that scale, the Great Attractor is far too local to drag the entire sample coherently. Shapley is also far too local to provide a simple explanation for a flow extending across such a vast region. The problem is easier to see if you think about distance from the supposed source. Gravity weakens with distance. For two isolated masses, Newton's familiar inverse square law tells us that the force falls as the square of the separation increases. Cosmology complicates that simple picture because we are not dealing with two isolated objects in empty space. We're dealing with an expanding universe filled with distributed matter, dark matter, and large-scale structure. Still, the basic lesson survives. A distant gravitational source has to be extremely massive to produce a strong effect across an enormous region. Move the source farther away, and you need more mass, then considerably more. Eventually, your explanation begins to create other observational problems. A mass concentration large enough to drive an enormous coherent flow inside the observable universe should usually leave other clues. It would contain or influence galaxies. It would affect gravitational lensing. It would contribute to the large-scale distribution of matter. It could produce signatures in surveys of clusters in the cosmic web. It might affect the microwave background in other ways. You cannot easily hide an absurd amount of gravitating matter and ask it to influence half the neighborhood without anyone noticing. Dark matter does not solve that problem automatically. The word dark can make it sound as though dark matter is an unlimited storage cupboard for missing gravity. If an observation needs more mass, perhaps we simply add more dark matter. But dark matter is not invisible to gravity. That is how we know it exists. A sufficiently huge dark matter concentration would affect the motion of visible matter around it and bend light passing through its gravitational field. Astronomers may not see dark matter glowing, but they can map its effects. So when the dark flow team argued that the distribution of matter in the observed universe could not account for the claimed motion, they were not merely saying that no bright object had been spotted in the correct direction. They were saying that the large-scale gravitational landscape we could infer did not contain an adequate source for a coherent motion of the reported magnitude and extent. That is a much more serious problem. One possible escape would be to assume there are enormous structures inside the observable universe that surveys have somehow missed. Astronomers do miss things. The history of the Great Attractor itself proves that. The plane of the Milky Way hides galaxies. Distant galaxies can be faint. Dust interferes with visible light surveys. Different wavelengths reveal different populations. But as surveys expanded into infrared, X-ray and radio wavelengths, and as maps of large-scale structure improved, hiding a structure big enough to explain the full dark flow claim became increasingly difficult. You could conceal some galaxies behind our own. You could underestimate a cluster. You might revise the mass of a supercluster. Explaining a coherent velocity across billions of light years is another level of problem. There is also an important statistical expectation. In the standard cosmological model, large-scale structure grew from the tiny density fluctuations visible in the cosmic microwave background. Some regions began slightly denser than average, others began slightly less dense. Over time, gravity amplified these differences. Those initial fluctuations predict not only where structure tends to form, but also the typical velocities that structures should develop. Smaller regions can have substantial bulk motion because their gravitational environment may be strongly unbalanced. As the region becomes larger, however, more independent density fluctuations are included. Pulls from different directions begin to average out. The expected bulk velocity decreases. This does not mean that a huge flow is mathematically forbidden. Cosmology deals in probabilities. An unusually large fluctuation can occur, but the larger and more coherent the flow becomes, the more unlikely it is under the standard statistical picture. The original dark flow claim therefore combined two uncomfortable features. The velocity was large, and the scale over which it supposedly persisted was enormous. Either one by itself might be easier to absorb. Together, they pushed the measurement toward a regime where ordinary structure inside the observable region seemed insufficient. At this point, it becomes tempting to imagine a giant hidden supercluster just beyond the farthest galaxies we can see. That image is useful only up to a point. The observable universe does not have a simple physical edge located just beyond the most distant galaxy in a telescope image. Our observational horizon is determined by the age of the universe, the finite speed of light, and the history of cosmic expansion. There may be far more universe beyond the region from which signals can currently reach us. If inflation occurred, the full cosmos may be vastly larger than our observable patch. A structure beyond the present horizon would therefore not be outside the universe in the ordinary sense. It would be outside the universe available to direct observation from here. But this creates an immediate difficulty. If something is now beyond our causal horizon, how could it be pulling galaxy clusters toward it? Gravity does not transmit information instantaneously. In general relativity, changes in the gravitational field propagate at the speed of light. You cannot place a new object beyond the horizon today and have Earth immediately begin responding to it. The more careful versions of the dark flow explanation therefore involve the early universe. The idea is not usually that an unseen supercluster is currently reaching across an impossible boundary and dragging galaxies toward itself. Instead, a very large-scale gravitational gradient could have existed when the universe was much younger, and when regions now separated beyond our horizon were connected differently. Inflation could then have stretched those regions apart. The motion left behind in our observable patch might survive as a kind of relic. In that picture, dark flow would be less like a present-day tug, and more like momentum inherited from the universe's earliest conditions. Imagine placing a tray on a table and giving everything on the tray a gentle push in one direction. Later, you separate the objects by enormous distances. Their common motion contains information about the earlier push, even though they are no longer interacting with the original source in the same way. The analogy is imperfect, but it captures the important distinction. A primordial flow does not require galaxies today to be feeling an impossible instantaneous force from outside the observable universe. It requires conditions before our present cosmic horizon became what it is. That possibility is one reason dark flow attracted theorists. If real, it might provide information about scales larger than the observable universe. Normally, cosmology has a frustrating limitation. We have one observable universe. We cannot step outside it. We cannot compare our cosmic region with another one from a convenient external viewpoint. We cannot fly beyond the horizon and send back photographs. If a large-scale motion preserved information about conditions outside our currently observable patch, it could provide an indirect window onto a part of reality that telescopes cannot simply image. That would be remarkable. it would also require extremely strong evidence. A measurement this consequential cannot rest comfortably on a faint statistical signal that different analysis methods treat differently. This is why the phrase, "too large for the known universe to explain," needs to be handled carefully. It does not mean scientists proved that every possible structure inside the observable universe had been catalogued and mathematically eliminated. It means that, under the interpretation proposed by the dark flow team, the observed distribution of matter and the expected large-scale fluctuations did not naturally produce the reported motion. That is a conditional statement. If the flow is real at that scale, then the source is difficult to explain with ordinary known structure. Remove the first part of that sentence and the whole mystery changes. And there was another reason to be cautious. The kinetic Sunyaev-Zeldovich signal being used was extremely small. The dark flow measurement depended on statistical filtering of the microwave sky at cluster positions. This was not the same as measuring 1,000 km/s velocity directly for each individual cluster. The physical velocity was inferred from a tiny temperature dipole. If the calibration linking that dipole to velocity was wrong, the estimated speed could change. If residual primordial microwave fluctuations remained after filtering, they could contribute to the signal. If the cluster sample behaved differently from the assumptions used in the analysis, that could matter too. The more dramatic the implied physics, the more attention these technical details received. Later measurements from Planck became especially important for this reason. Planck observed the cosmic microwave background with greater sensitivity and broader frequency coverage than WMSP. A Planck analysis searched for peculiar velocities and bulk flows using galaxy clusters and did not find a significant large-scale flow of the magnitude associated with the original dark flow claim. In a blind search, the study placed a 95% confidence upper limit of 254 km/s on the bulk flow amplitude for its cluster sample, and concluded that its results were consistent with the standard lambda-CDM cosmological model. That did not prove that every large-scale velocity measurement in cosmology was trivial. It did mean that the strongest version of dark flow had failed an important independent test. The mystery therefore split into two possible stories. In one story, there really is an anomalous large-scale motion, but current methods have not yet measured it consistently. In the other, the original signal was produced by some combination of noise, foregrounds, filtering, calibration, or statistical chance, and there is no exotic flow requiring anything beyond the observable horizon. The second possibility is less dramatic, but it would still be a useful scientific result. Discovering why a method produced a false signal can improve later measurements. It can reveal hidden biases. It can sharpen our understanding of the microwave sky. Science does not lose when an exciting anomaly disappears. It simply changes what has been learned. Still, if we temporarily follow the original dark flow interpretation, the next question becomes unavoidable. Before looking beyond the observable universe, did astronomers really exhaust the structures closer to home? Could the Great Attractor, Shapley, or some combination of giant superclusters create more motion than expected? Could unseen dark matter bridge the gap? Could multiple overdense regions line up in a way that imitates one enormous pull? These possibilities matter because the universe already contains gravitational structures so large that their numbers are difficult to picture. A galaxy can contain hundreds of billions of stars. A rich cluster can contain hundreds or thousands of galaxies. Superclusters and walls can extend across hundreds of millions of light years. When scales become that large, it is reasonable to wonder whether the ordinary cosmic web might be capable of more than a simplified calculation suggests. The answer requires looking closely at the main suspects rather than treating the Great Attractor as a single mysterious object. There is the Norma cluster buried behind the Milky Way. There is the broader Hydra Centaurus region. There is Shapley farther out. There are voids whose missing gravitational pull helps shape our motion. There are filaments connecting dense regions. and there is dark matter distributed through all of them. Together they produce a complicated velocity field rather than one clean arrow. That complexity is exactly why the dark flow claim was so provocative. The claimed direction lay in a part of the sky already crowded with known large-scale attractions, making it easy to assume the mystery was simply another version of the Great Attractor story. But the reported distance range was far larger. A structure capable of explaining a local flow does not automatically explain a coherent motion measured billions of light-years away. So the investigation has to move through these gravitational suspects one at a time, beginning with the Great Attractor itself, then pushing farther toward Shapley and beyond to see where ordinary large-scale structure stops being a comfortable explanation and where the truly speculative possibilities begin. The first suspect on any sensible list was the Great Attractor, because astronomers already knew that something in that part of the sky was affecting the motion of the Milky Way and many nearby galaxies. Long before anyone used the phrase dark flow, researchers had noticed that our local region was not simply following the expansion of the universe. After the expected expansion was removed from the measurements, a substantial peculiar velocity remained. The Milky Way, Andromeda, and the rest of the local group are moving relative to the cosmic microwave background at several hundred kilometers per second. That motion does not point randomly across the sky. A significant part of it is directed toward the general region of the constellations Centaurus and Hydra. That made astronomers suspicious. Something with a considerable amount of mass appeared to be located in that direction. Unfortunately, the Milky Way itself was blocking the view. The plane of our galaxy contains huge numbers of stars, clouds of gas and interstellar dust. Looking through it toward distant galaxies can be like trying to study the houses across a city while standing behind a brightly illuminated hedge. The houses are still there. The hedge has simply chosen an inconvenient location. Astronomers had given this obscured region another memorable name, the Zone of Avoidance. Visible light surveys found fewer external galaxies there, not because the universe had suddenly run out of galaxies, but because our own galaxy was getting in the way. This created a frustrating situation. The motions of nearby galaxies suggested that a large concentration of mass existed in a particular direction, while ordinary telescopes had trouble seeing what was actually there. The hidden concentration became known as the Great Attractor. The name can create the wrong impression. It sounds as though there must be one enormous object sitting in space, perhaps a black hole of ridiculous size pulling galaxies toward itself. That is not what the Great Attractor is. It is better understood as a broad region of enhanced mass associated with clusters, galaxies, dark matter, and larger structures in the Hydra-Centaurus direction. NASA has described the Great Attractor as a structure much larger than an individual galaxy, with the rich galaxy cluster Abell 3627, also called the Norma cluster, located near its central region. X-ray observations helped reveal that Norma contained far more galaxies in mass than earlier visible light surveys had suggested, because it lies partly hidden behind the Milky Way. The Norma cluster is a serious object. A rich galaxy cluster contains hundreds or even thousands of galaxies, along with enormous quantities of hot gas and dark matter. The combined mass can strongly influence surrounding galaxies. Once Norma and neighbouring structures were mapped more carefully, part of the mysterious local motion became much easier to understand. There really was a large concentration of matter in approximately the direction astronomers had inferred from galaxy velocities. That was reassuring. Gravity had pointed toward something, and astronomers eventually found something. But the Great Attractor did not solve everything. As observations extended farther into space, researchers found that the velocity field continued beyond the Great Attractor region. Some galaxies appeared to be responding to mass located farther away. The Great Attractor itself seemed to be part of an even larger network of motion. This led attention toward another enormous structure, located considerably farther from us, the Shapley concentration. Shapley had actually been noticed much earlier. The astronomer Harlow Shapley identified an unusual concentration of galaxies in this region in the 1930s, long before modern large-scale surveys could reveal its true scale. Today, Shapley is recognised as one of the most impressive concentrations of galaxies in the relatively nearby universe. It contains numerous galaxy clusters packed into a region that is substantially denser than average. Estimates of its total mass depend on exactly how the structure is defined, but studies have placed it at around a few times 10 quadrillion solar masses. One analysis estimated a total mass near 1.8 times 10 to the 16 solar masses, depending on the cosmological parameters used. That is an amount of matter for which ordinary comparisons stop being especially helpful. You could say it is equivalent to tens of quadrillions of suns. That is accurate. It is also a number the human brain will politely accept without doing anything useful with it. What matters is that Shapley is sufficiently massive to influence the motion of galaxies across a very large region, and it lies in broadly the same part of the sky toward which our local motion points. Naturally, astronomers wondered whether the Great Attractor was only part of the explanation, and Shapley supplied the rest. The geography seems encouraging at first. Here we are in the local group. Farther away lies the Great Attractor region. Beyond that lies Shapley. The motions appear to lead generally in that direction. It is tempting to imagine a simple hierarchy in which the Milky Way falls toward the Great Attractor, while the Great Attractor falls toward Shapley. There is some truth in that picture, but the actual velocity field is more complicated. Different studies have estimated different contributions from Shapley to our peculiar velocity, because the result depends on how mass is reconstructed and how the surrounding structures are treated. Some analyses have found a substantial contribution from distant structures in the Shapley region, while others have estimated a considerably smaller direct effect on the local group. What is clear is that Shapley is an important part of the large-scale gravitational landscape, but it is not a convenient single answer to every unexplained motion. There is a good reason for the disagreement. Space between us and Shapley is not empty. There are other clusters, there are filaments, there are walls of galaxies, there are underdense regions. There is dark matter distributed throughout the cosmic web. Every one of these contributes to the gravitational field. Trying to assign a precise fraction of our motion to one distant structure can therefore become a bit like asking exactly which person in a crowd caused you to move when everyone was leaning against everyone else. You can identify the strongest influences. Separating them perfectly is harder. In 2014, a team led by Brent Tully introduced a particularly useful way of visualizing our local large-scale environment. Rather than defining a supercluster simply by drawing a boundary around a concentration of galaxies, the researchers used peculiar velocities. They examined how galaxies move after cosmic expansion is removed. Regions where the velocity streams converge can be treated like gravitational drainage basins. If nearby galaxies tend to flow toward the same internal region, they can be grouped within one larger dynamical structure. Using this approach, the researchers defined our home supercluster and named it Laniakea. Laniakea is enormous. The original analysis described a structure roughly 160 megaparsecs across, containing about 100,000 large galaxies and a mass around 100 quadrillion times that of the Sun. It includes the Virgo region, where the local group resides, as well as the Norma, Hydra, and Centaurus clusters associated with the Great Attractor. The map produced by that work is useful because it changes the way the Great Attractor should be imagined. The Great Attractor is not some separate monster sitting outside our cosmic neighbourhood. It is part of the larger flow pattern within Laniakea. Galaxies in different parts of the region have peculiar velocities that trace paths through the underlying gravitational landscape. Some streams converge toward the vicinity of the Norma and Centaurus regions. Other flows respond to structures beyond Laniakea. The analogy used by the researchers resembles a watershed. On Earth, rain falling on one side of a mountain ridge eventually flows into one river system. Rain landing on the other side may drain into a completely different basin. You can define the boundary between the two by following the direction of the water. Laniakea was defined in a similar way using galaxy velocities instead of rain. No umbrellas required. This view also makes another point clear. Our supercluster is not gravitationally isolated. Matter beyond it still contributes to the motion. The 2014 reconstruction found external flows heading toward more distant structures, with Shapley playing an especially important role in the surrounding large-scale landscape. So perhaps Shapley was the true attractor behind everything. That would certainly simplify the story. Unfortunately, the universe had another complication ready. Not all large-scale motion comes from overdense regions. Voids matter too. A cosmic void is a region containing much less matter than average. Voids can span enormous distances. They are not completely empty, but compared with filaments and clusters, they are sparsely populated. At first, an underdense region might seem irrelevant to a discussion about gravitational attraction. Less matter means less gravity. Exactly. And that difference matters. Imagine placing yourself between two equally strong gravitational concentrations. If both pull with the same strength in opposite directions, the forces can balance. Now remove most of the mass from one side. The remaining concentration does not become stronger, but your net acceleration points toward it, because the opposing pull has weakened. An observer describing only the motion might say that the object is being pulled toward the dense side. Another equally valid description is that the gravitational influence normally supplied by matter on the empty side is missing. This became important in attempts to explain the motion of the local group. In 2017, Yehuda Hoffman, Daniel Pomered, R. Brent Tully, and Hélène Courtois reconstructed the local velocity field and identified a large underdense region in roughly the opposite direction from our motion. They called it the dipole repeller. The name does not mean the void contains a repulsive force. Ordinary gravity is still doing the work. There is simply less gravitational attraction coming from that part of the universe. The reconstruction suggested that the Shapley concentration pulling from one side and the large underdensity corresponding to the dipole repeller on the other side contributed roughly equally to the observed large-scale motion associated with the cosmic microwave background dipole. This made the local motion much easier to understand as a combination of influences rather than a search for one hidden object. Shapley pulls. The underdense region provides less counterpull. Other clusters and filaments contribute additional terms. The Milky Way responds to the sum of everything. That is much closer to how gravity actually operates in the cosmic web. There are other structures in the neighbourhood as well. The Perseus-Pisces supercluster forms another prominent concentration of galaxies. There are major voids surrounding various filaments. There is the local void close to our own group. Coma and other rich clusters contribute to the wider distribution. Modern reconstructions of the nearby universe routinely recover several of these concentrations and voids together, including Virgo, Centaurus, Coma, Shapley, Perseus-Pisces, and the dipole repeller. Then there is the part of the sky that continues to cause trouble, simply because the Milky Way refuses to become transparent. The zone of avoidance still hides significant large-scale structure. In 2016, astronomers reported the discovery of another major concentration crossing the galactic plane in the constellation Vela. The Vela supercluster lies much farther away than the Great Attractor. Observations revealed a large overdensity extending across the obscured region, with wall-like structures and clusters at a mean recession velocity of about 18,000 kilometers per second. Its location was especially interesting because it lies near the direction where some peculiar velocity studies had suggested that additional gravitational influence might be missing from existing surveys. Later work found kinematic evidence supporting the existence of this hidden concentration. Radio observations have continued mapping the Vela region because hydrogen emission can reveal galaxies through parts of the Milky Way that are extremely difficult to survey optically. Recent studies still describe Vela as potentially relevant to residual bulk flows, although estimates of its effect on the local group are much smaller than the extreme velocities proposed for dark flow. This is an important example because it demonstrates why astronomers cannot simply assume that every large structure inside our observable region has already been found. The sky has blind spots, surveys have limits, a concentration of galaxies really can hide behind our own galaxy for decades. That naturally raises the possibility that the original dark flow signal might have been caused by some combination of overlooked structures. Perhaps Shapley was more influential than expected. Perhaps Vela supplied additional gravitational acceleration. Perhaps dark matter extended beyond the visible concentrations. Perhaps other superclusters were hiding in poorly surveyed regions. There is nothing unreasonable about checking these possibilities. They are exactly what should be checked before proposing anything exotic. But the scale problem remains. The Great Attractor is relatively nearby on cosmological scales. Shapley is farther away. Vela is farther still. All can influence peculiar velocities in our general region. None naturally explains why galaxy clusters located more than 2 billion light-years away from us, and separated from one another by enormous distances, should share a strong coherent motion with approximately the same large-scale axis. That was what made the original dark flow interpretation different from ordinary local flow studies. Suppose every cluster in the Kashlinsky sample had been relatively nearby. Then the Great Attractor, Shapley, Vela, voids, and other structures would be obvious places to search for the source. But the reported signal persisted as the cluster sample was divided into increasingly distant ranges. NASA's 2010 description of the result placed the claimed flow beyond 2.5 billion light-years along an axis roughly associated with Centaurus and Hydra. A mass concentration 100 or 200 million light-years from the Milky Way cannot easily give clusters billions of light-years away the same peculiar velocity. Those distant clusters have their own gravitational neighbourhoods. They have their own superclusters, their own filaments, their own voids. Some are nowhere near the Great Attractor in three-dimensional space, even if their projected positions on our sky appear to participate in the same statistical dipole. This is where thinking in terms of a flat sky map becomes dangerous. Two objects can appear next to each other on the sky and actually be separated by billions of light-years in depth. The constellations themselves work this way. Stars that look like neighbours from Earth are often located at completely different distances. The same is true when looking toward galaxy clusters. Saying that several clusters appear in the direction of Centaurus does not mean they are all physically sitting beside the Great Attractor. Some may be hundreds of millions or billions of light-years behind it. Gravity depends on actual three-dimensional separation, not where something happens to appear on an astronomer's map. That means an attractor capable of influencing the entire proposed dark flow sample would have to operate on a scale much larger than any ordinary nearby supercluster. It could not simply be a somewhat more massive version of Norma, nor could Shapley be enlarged slightly and asked to do the job. The mass required would become enormous, and a concentration that large within the observable universe should influence other measurements. Its galaxies would affect large-scale surveys, its dark matter would affect gravitational lensing, its gravitational potential would influence surrounding structures. Its presence would be difficult to hide entirely. This is also why dark matter cannot simply be placed wherever the calculation needs extra gravity. Dark matter does not emit light, but it gravitates. If enough of it were concentrated in one region to produce a tremendous flow across billions of light-years, visible galaxies and light passing through the region would respond. We would expect other observational consequences. There is another distinction worth making here. Large-scale flows have continued to be studied using galaxy surveys, supernova distances, peculiar velocity catalogues, and other methods. Some analyses have reported bulk flows larger than simple predictions at particular scales. Those results are interesting, but they are not automatically the same thing as Kashlinsky's dark flow. A flow measured across a few hundred million light-years can potentially arise from structures such as Shapley, Vela, and the surrounding cosmic web. A strong coherent flow extending across several billion light-years is a much more demanding claim. Mixing the two makes the evidence appear stronger than it is. A nearby current does not prove an ocean-wide current exists. The Great Attractor provides perhaps the best lesson. When astronomers first saw unexplained galaxy motion in its direction, they eventually discovered genuine hidden mass. That might make it tempting to assume that dark flow is simply the same story on a larger scale. First unexplained motion, then a hidden attractor. Eventually a telescope discovers it. But there is an important difference. The Great Attractor lay inside a region that could, in principle, be observed once astronomers used the right wavelengths and better surveys. The source was hidden by dust and stars, not beyond a fundamental observational horizon. Dark flow, if the original interpretation were correct, seemed to require influence on such a large scale, that the source might lie outside the region from which we can currently receive direct information. That is a very different kind of hidden. One object is behind a curtain, the other may be beyond the part of the stage visible to us at all. And before moving that far, there is still one final scientific caution to keep in place. The fact that known structures struggle to explain dark flow does not make an unseen external structure the default answer. It strengthens the case for checking the measurement itself. Planck's later failure to recover the enormous flow remains a major reason the original claim is disputed. If the signal ultimately came from filtering or statistical effects rather than real cluster velocities, then none of these cosmic suspects needs to explain it. The Great Attractor is real. Shapley is real. Laniakea is a useful dynamical description of our home region. The dipole repeller reflects a genuine attempt to reconstruct the influence of a major underdensity. Vela is a real large-scale overdensity that was partly concealed by the Milky Way. All of them help explain how complicated cosmic motion can become without requiring new physics. What they do not provide is a confirmed explanation for the original dark flow signal across billions of light years. If we temporarily accept that signal and ask where an influence of that scale could come from, the investigation is forced beyond the familiar map, not necessarily beyond the universe itself, but beyond the observable portion available to us. That immediately creates another question, because outside the observable universe is one of those phrases that sounds simple until cosmologists begin defining what observable actually means. There may be far more space beyond our horizon than we can see, filled with galaxies, clusters, and structures following the same physical laws as everything around us. Whether any of those regions could have left a measurable influence inside our own observable patch depends on when they were connected to us, how cosmic expansion separated them, and what happened during the earliest fractions of the universe's history. The phrase, beyond the observable universe, can easily sound as though we are talking about somewhere outside existence itself, but that is not what astronomers mean. The observable universe is simply the part of the cosmos from which information has had enough time to reach us. That difference changes almost everything. The universe is about 13.8 billion years old, but the observable universe is not only 13.8 billion light years across. Space has been expanding while light travels through it. A galaxy whose ancient light has been travelling toward us for more than 13 billion years is now much farther away than 13 billion light years. When cosmologists account for the expansion of space, the present diameter of the observable universe is estimated to be about 92 billion light years. Neeson notes that we have no reliable measurement of the size of the entire universe and do not currently know whether it is finite or infinite, so the region we can see may be only part of something much larger, possibly a very small part. Imagine standing in the middle of a large field on a foggy morning. You can see the grass immediately around you, perhaps a few trees, maybe a fence in the distance. Beyond that, everything disappears into the fog. The visible circle around you is not the entire field. It is simply the portion from which enough light reaches your eyes without being completely obscured. The universe has no ordinary fog marking its observable limit, but the general idea of limited visibility is useful. Our cosmic horizon is a limit on information. It is not known to be a physical wall. There is no reason to imagine galaxies reaching the edge and stopping. There is no border patrol. There is no sign telling photons to turn around. There may simply be regions so distant that signals from them have not had enough time to reach us. The difficult part is that there are several kinds of horizons in cosmology, and they are easy to mix together. One important limit comes from the finite age of the universe. Light travels at a finite speed. If something is sufficiently far away, light emitted from it has not had enough time to arrive here. That produces what cosmologists call a particle horizon. It defines, roughly speaking, the greatest distance from which information could have reached us during the history of the universe. Then there is the cosmic microwave background. As we have already seen, the CMB comes from a time about 380,000 years after the Big Bang, when the universe cooled enough for photons to travel freely. That creates an observational surface called the surface of last scattering. When we look at the CMB, we're not looking at the absolute edge of the universe. We are looking at the earliest electromagnetic light that can travel freely to us. Before that time, the universe was filled with an opaque plasma. Ordinary photons could not travel directly across great distances. A larger telescope cannot simply look through that period, because the problem is not that the light is too faint. The light was repeatedly scattered. The universe itself was opaque. This means the CMB acts almost like a screen hiding earlier electromagnetic history. There may eventually be other ways to investigate earlier times, perhaps through primordial gravitational waves or other indirect signals, but ordinary light reaches a natural limit. Beyond the CMB in time lies the earlier universe. Beyond our particle horizon in space may lie more universe. Those are related ideas, but not the same thing. Once that distinction is clear, the possibility of something existing beyond our observable region becomes much less exotic. In fact, most modern cosmological thinking allows for it quite naturally. NASA describes the universe as potentially much larger than what we can observe, while ESA has long noted that observations can place lower limits on the total size, without telling us whether the whole cosmos is finite or infinite. Suppose the full universe is infinite. Then our observable region would be a finite bubble of accessible information inside an unlimited cosmos. There could be galaxies beyond our horizon. Beyond those could be more galaxy clusters. Beyond those, more filaments, voids, stars, planets, black holes and regions that will never appear in any telescope operating from Earth. Nothing special would need to happen at our observational boundary. The cosmic web might simply continue. If the universe is finite instead, it could still be substantially larger than the region we can see. Its global shape could also be more complicated than an ordinary sphere. Cosmologists study possibilities involving different geometries and topologies, although current observations show that the observable universe is very close to spatially flat on large scales. None of this means scientists know what actually exists beyond the horizon. That is the frustrating part. You can write equations describing larger universes. You can test whether observations inside our region are consistent with those models. But direct observation requires information to reach you. If no light, gravitational wave, particle, or other causal signal from a region can ever arrive here, then that region cannot be examined in the usual way. This is why statements about what lies beyond the observable universe have to be made carefully. There is probably more universe beyond what we see is a reasonable inference within many cosmological models. There is a giant supercluster, exactly 40 billion light-years beyond our horizon, pulling on us right now, would be a much stronger claim. Dark flow became interesting because it appeared, at least in the original interpretation, to offer a possible way around some of that observational limitation. If galaxy clusters throughout our visible region retained a common motion caused by conditions on scales larger than the observable universe, then the motion itself could function as indirect evidence. We would not see the source, we would see its effect. This sounds similar to how dark matter was inferred. Astronomers could not initially observe dark matter directly, but stars and galaxies moved as though additional mass were present. gravitational lensing later provided another way of mapping that unseen mass. Dark flow, if real, would be more difficult because the hypothetical source could lie beyond the horizon rather than merely being invisible. The natural objection is immediate. If something is beyond the observable universe, how can its gravity reach us? Gravity does not act instantaneously. Einstein's theory of general relativity does not allow a gravitational change to communicate information arbitrarily fast across space. Gravitational disturbances propagate at the speed of light. If a giant mass suddenly appeared today in a region completely outside our causal horizon, Earth would not immediately feel a new pull from it. Dark flow proposals did not require that. The idea was tied to the early universe. This is where inflation enters. Cosmic inflation is the hypothesis that the very young universe underwent a brief period of extraordinarily rapid expansion. Exactly what drove inflation remains unknown, but the idea helps explain several features of the cosmos, including why the observable universe is so geometrically flat, and why regions now separated by enormous distances have such similar large-scale properties. ESSA describes inflation as a period in which extremely small primordial fluctuations were stretched to cosmological scales. Those fluctuations later provided the seeds from which galaxies and clusters grew. Before inflation stretched space enormously, regions now very far apart could have occupied a much smaller physical volume. That matters for causality. Consider two regions of the sky that are now separated by tens of billions of light years. Today, they may be unable to communicate directly. Yet in the very early universe, the material that eventually formed those regions could have been much closer together. Conditions established at that early stage could therefore appear correlated across distances that are now enormous. Inflation essentially takes tiny patterns and stretches them. One of its great successes is explaining how microscopic fluctuations could become the initial variations that eventually form the cosmic web. A similar line of reasoning motivated some interpretations of dark flow. Suppose the region that became our observable universe was once part of a much larger pre-inflationary environment. Suppose that environment was not perfectly uniform. Perhaps there was more matter or energy in one direction on scales much larger than the patch that eventually became visible to us. That imbalance could create a gravitational gradient. Matter inside our patch might receive a small common velocity. Inflation would then expand the patch dramatically. The source of the original gradient could be carried far beyond our current horizon, but the motion established before or during that early stage might remain. Billions of years later, galaxy clusters forming from matter inside our observable region could still share part of that primordial velocity. This was one of the possibilities associated with the original dark flow interpretation. NASA's announcement describing Kashlinski's 2008 result specifically noted the suggestion that the clusters might be responding to matter pushed beyond the observable universe by inflation, and that, if so, the motion might contain information about conditions before inflation. Notice how different that is from the common picture of an enormous hidden object pulling galaxies toward itself right now. The popular version imagines a giant attractor sitting outside our visible universe like a magnet beyond a curtain. The proposed cosmology was more subtle. The flow could be a relic, a leftover velocity, an imprint created when the causal arrangement of the universe was very different. A simple everyday analogy would be giving a group of objects a push before separating them. Imagine placing several hundred toy boats together in a large swimming pool. Before they spread apart, a broad current gives all of them a slight motion toward one side. Later, the boats drift far away from one another. The original current is no longer acting on them in exactly the same way, yet each boat still carries some momentum from what happened earlier. If you measured them later and found a shared component of motion, you might infer something about the earlier condition of the pool. Galaxies obviously do not preserve velocities as simply as toy boats. Gravity continually alters their motion. The universe expands, structures form, clusters interact with their local environments. but a sufficiently large primordial mode could, in principle, leave a coherent signature. Cosmologists sometimes discuss fluctuations with wavelengths larger than the observable horizon. These are often called superhorizon modes. A wavelength in this context does not mean a literal wave that you could watch moving past Earth. It describes the spatial scale of a fluctuation in density or gravitational potential. If the wavelength is much larger than our observable region, we would see only a small portion of it. Imagine standing on a very long, gently sloping hill. If the hill extends thousands of kilometers, you cannot see the entire shape. From your local position, the surface may simply appear to tilt slightly in one direction. A superhorizon fluctuation could behave somewhat similarly. Across the limited region we observe, a much larger variation might appear as a broad gravitational gradient rather than a complete pattern. This kind of possibility makes cosmologists interested in very large-scale anomalies. If a coherent signal exists across nearly the entire observable sky, it may contain information about scales larger than the region being measured. But there is a major difficulty. Inflation was introduced partly because it tends to make the observable universe extremely uniform. If inflation lasted long enough, many irregularities that existed beforehand would be stretched far beyond our observable patch and diluted. Our region would appear smooth. That is broadly what we see. The cosmic microwave background is extraordinarily uniform, with temperature fluctuations only around 1 part in 100,000 after the large dipole caused by our own motion is removed. Planck's measurements provide strong overall agreement with the standard cosmological model and with a nearly uniform early universe, even though some large-scale features and anomalies have continued to attract discussion. For a pre-inflationary feature to leave a measurable dark flow signal today, inflation would need to preserve just enough information for the effect to survive without producing other discrepancies that observations would already have revealed. That is possible in particular theoretical constructions. It is not an automatic consequence of inflation. This distinction matters because there is a tendency to use inflation as a universal explanation for anything strange occurring at large distances. See an unusual pattern. Inflation. See a directional anomaly. Inflation. Misplace your keys. Probably not inflation. A successful theory has to do more than provide a word. It has to make predictions consistent with multiple observations. A dark flow explanation involving pre-inflationary structure would need to reproduce the claimed cluster motion, while remaining compatible with the microwave background, galaxy distribution, large-scale structure, and other cosmological measurements. The same caution applies when the discussion moves toward a multiverse. Inflationary cosmology has inspired models in which our observable region is one part of a much larger collection of regions, sometimes described as bubble universes. In some versions of eternal inflation, inflation continues in parts of a larger space-time while ending locally in regions like ours. This creates a potentially enormous structure containing many causally separated domains. It is an intriguing idea. It is also much more speculative than the statement that there is probably more ordinary universe beyond our observable horizon. Those two claims should not be treated as interchangeable. Something beyond the observable universe could simply be more of the same cosmos, more space, more galaxies, more dark matter, more cosmic web. The multiverse introduces additional assumptions about the global behavior of inflation and the existence of separate domains that may have different histories or physical conditions. Dark flow was sometimes discussed in connection with these ideas because any apparent influence from beyond our horizon naturally encourages speculation about a larger cosmic environment. But the original measurement did not prove another universe existed. It did not prove a collision between universes. It did not show that another cosmic bubble was dragging galaxies toward it. Even if the signal had been confirmed, determining its origin would have required substantial additional evidence. There are also possible signatures researchers have considered when searching for physics beyond our observable patch. Some models predict unusual patterns in the cosmic microwave background. Others predict large-scale asymmetries. Hypothetical collisions between inflationary bubble regions might produce circular or disk-like features in the CMB. Researchers have searched for such signatures, but no widely accepted evidence of another universe has emerged. The CMB remains our strongest observational connection to the earliest accessible phases of cosmic history, and ESA emphasizes that the period before the formation of the microwave background is much more uncertain than later epochs. That uncertainty gives theorists room to explore possibilities. It does not give us permission to treat every possibility as an observation. There is another strange consequence of cosmic expansion that makes the horizon question even more interesting. The observable universe is not static. The set of events whose light can reach us changes with cosmic time. At the same time, accelerated expansion driven by dark energy means that extremely distant regions can eventually become permanently inaccessible to future communication. Some galaxies we see today emitted their light when they were much closer to us in terms of cosmic geometry. Their present-day descendants may already be receding in a way that prevents signals emitted now from ever reaching Earth. We can see their past without ever receiving information about some portions of their future. This is a peculiar feature of an expanding universe. Visibility does not mean permanent communication. Distance is not simply a number measured with an enormous ruler. It depends on how space expands while signals travel. These ideas make the word outside especially dangerous. There may be galaxies beyond the distance from which light has reached us. There may be regions that were once causally connected to the material in our observable patch. There may be regions whose future signals will never arrive. There may be far more universe than any civilization in the Milky Way could ever observe, even if it survived for an unimaginably long time. That does not place those regions in another dimension or outside physical reality. They may simply be inaccessible portions of the same space-time. If dark flow had provided reliable evidence for such a region, it would have been one of the most remarkable achievements in observational cosmology. We would be learning about something we could not photograph by measuring a leftover influence inside the region we can see. That is why the original claim attracted attention far beyond the small community studying peculiar velocities. It seemed to offer a possible observational handle on the global universe, a way to ask whether our visible patch sits inside something much larger and uneven, a possible clue about conditions before inflation erased most traces of whatever came earlier. The temptation to push the interpretation as far as possible was understandable, but an extraordinary interpretation becomes worthwhile only if the underlying measurement is secure. And that is where dark flow runs into its central problem. The same signal that seemed so persistent to the team that discovered it did not appear with the same strength when other groups used different methods and later data. Some analyses questioned the statistical significance. Others argued that the filtering procedure could create or exaggerate the apparent dipole. The conversion from a temperature signal to a physical cluster velocity introduced substantial uncertainty. Then Planck produced a more sensitive microwave map and failed to find convincing evidence for the enormous coherent bulk flow originally reported. At that point, the question changed. Instead of asking only what could exist beyond the observable universe, cosmologists had to ask something more basic first. Was dark flow actually there? That disagreement is not a minor technical footnote. It determines whether we are discussing a real cosmic current in need of a remarkable explanation or a very difficult measurement that briefly looked like one, and the evidence on both sides has to be separated carefully before any conclusion about unseen regions of the cosmos can carry much weight. Once the idea of dark flow had entered cosmology, the obvious next step was not to invent something beyond the observable universe. It was to try very hard to make the signal disappear. That may sound like an odd way to do science. If you have discovered something interesting, surely you would want to protect it. Scientists usually do the opposite. A result becomes much more valuable if it survives attempts to break it. Change the assumptions. Use a different statistical method, remove part of the data, add more data, replace the instrument, ask another team to perform the analysis independently. Simulate thousands of universes in which the phenomenon does not exist, and see how often something similar appears by chance. If the signal survives all of that, confidence increases. If it disappears, then you have probably learned something about the measurement rather than the universe. Darkflow quickly became a perfect example of this process, because almost every important part of the measurement could be questioned. Remember what the researchers were actually trying to detect. They were not watching galaxy clusters move across the sky. Even a cluster travelling at 1,000 kilometers per second would appear almost stationary at cosmological distances during a human lifetime. Instead, the claimed motion was inferred from an extremely weak temperature signal in the cosmic microwave background at the positions of galaxy clusters. That signal was associated with the kinetic Sunyaev-Zeldovich effect. And the kinetic Sunyaev-Zeldovich effect is difficult to measure because it does not provide a convenient bright signature. The thermal Sunyaev-Zeldovich effect is easier in one important respect. It changes the spectrum of the cosmic microwave background in a characteristic way because very hot electrons in a galaxy cluster transfer energy to microwave photons. Different observing frequencies therefore help astronomers separate the thermal effect from other signals. The kinetic effect is more troublesome. It mainly shifts the temperature of the CMB without producing the same distinctive spectral distortion. In other words, a small kinetic signal can resemble an ordinary temperature fluctuation already present in the cosmic microwave background. That is inconvenient when the sky is full of ordinary temperature fluctuations. It is a little like searching for one person in a stadium who's wearing a white shirt, when several thousand other people have also chosen white shirts. The Darkflow team dealt with this by filtering the microwave maps and combining measurements from many clusters. If the unwanted CMB fluctuations were sufficiently reduced and the clusters shared a common velocity, a dipole should remain at the cluster positions. Kashlinsky and his collaborators argued that this is what they found. Critics immediately asked whether the filtering had actually removed enough of the primordial CMB. This became one of the central disagreements. In 2009, Ryan Keisler re-examined the statistical significance of the original Darkflow measurement. One of his main concerns involved correlations in the microwave background. The same CMB sky is observed by the different WMAP channels. The primordial temperature fluctuations are therefore not independent noise that disappears simply because several frequency maps are combined. Keisler argued that once the CMB contribution was handled appropriately, the statistical significance of the Darkflow detection fell considerably. The supposed signal in that analysis was no longer compelling evidence for a real bulk flow. Later papers by other groups also failed to recover the Darkflow with the significance claimed by Kashlinsky's team. By 2013, a published review of related KSZ bulk flow work noted that studies by Keisler, Osborne and collaborators and Modi and Hadjian had not independently confirmed the original large-scale flow. Kashlinsky and his colleagues disagreed with those criticisms. They argued that some of the alternative analyses were not testing exactly the same statistic or were using filters that removed part of the signal they were trying to detect. This is where the disagreement became technically complicated. Two groups could begin with almost the same microwave maps and almost the same galaxy clusters, then make different choices about filtering and error estimation and reach very different conclusions. That does not mean one group was simply looking at the sky incorrectly. When the desired signal is much smaller than the background, the analysis method becomes part of the experiment. Imagine trying to remove music from a recording so that you can hear a quiet conversation happening underneath it. One audio filter may remove the music extremely well, but also remove part of the voices. Another may preserve the voices but leave enough music behind to create false patterns. Both people working on the recording may genuinely believe their method is better. The only satisfying solution is to find a cleaner recording. For Darkflow, that cleaner recording was supposed to come from Planck. The European Space Agency's Planck satellite was designed to measure the cosmic microwave background with much greater detail than previous missions. It observed the sky across 9 frequency bands. Its angular resolution and sensitivity allowed much more precise studies of the primordial microwave fluctuations and of foreground signals. When Planck began returning results, researchers suddenly had a new dataset with which to repeat the dark flow test. This was important because WMAP and Planck were different instruments. They had different detectors, different observing strategies, different frequency coverage, different noise properties. If the same cluster dipole appeared independently in both, the argument that it came from a peculiarity of WMAP would become much weaker. If Planck did not see it, the original interpretation would face a serious problem. In 2013, the Planck collaboration published an analysis specifically examining peculiar velocities of galaxy clusters. The team used Planck observations together with a large catalogue of X-ray detected clusters and applied several filters designed to extract the kinetic Sunyaev-Zeldovich signal. They looked for average radial velocities, velocity dispersions, and bulk flows at different distances. The result was not what supporters of dark flow had hoped to see. Planck reported no detection of a bulk flow in the cluster sample at any of the scales examined. In a blind search, the researchers placed a 95% confidence upper limit of about 254 km per second on the bulk flow amplitude. They concluded that the results were consistent with the standard lambda-CDM cosmological picture and with a universe that is approximately homogeneous on very large scales. That number is worth comparing with the earlier claim. Dark flow had been associated with velocities approaching roughly 1,000 km per second. Planck's blind bulk flow limit was much smaller. If you were hoping for a straightforward confirmation, this was not it. For many cosmologists, the Planck results substantially weakened the case for dark flow. The simplest interpretation was that the enormous coherent motion reported from the WMAP analysis was not a real motion of galaxy clusters. Perhaps the original statistical significance had been overestimated. Perhaps residual CMB fluctuations contributed to the dipole. Perhaps some feature of the filtering method mattered. Perhaps converting the measured temperature dipole into an actual velocity introduced larger uncertainties than initially appreciated. This is normally the point in the popular version of the story where someone says, Planck disproved dark flow. The real history is less tidy. The original team did not agree that Planck had disproved their measurement. Fernando Atrio Barandella, Alexander Kashlinsky, Harold Eberling, Dale Fixon, and Dale Kosevsky performed their own analysis using the final 9-year WMAP maps and the first Planck data releases. Their paper appeared in 2015. They used a catalogue of 980 galaxy clusters and applied the filtering procedure developed in their earlier work. According to their analysis, the dipoles found in WMAP and Planck were consistent with one another. They also reported that the signal was similar in direction and amplitude to their previous measurements. Their Planck analysis produced a dipole whose statistical significance they described as better than 99%. They further argued that the measured dipole did not vary with frequency in the way a residual thermal Sunyaev-Zeldovich signal should, and that the effect was strongest for the most massive and X-ray luminous clusters. So Planck had now apparently produced two answers. One Planck analysis said there was no significant dark flow. Another analysis of Planck maps said a cluster-associated dipole was still there. That sounds absurd until you remember that satellites do not write conclusions. People analyse their measurements. The disagreement was about what statistics should be measured, which filter should be applied, how errors should be estimated, and how a residual temperature dipole should be translated into cluster motion. The Planck collaboration's method was designed to estimate peculiar velocities using several approaches. The dark flow team's method was designed specifically to reproduce the statistic they had developed with WMAP. Those were not identical procedures. Atrio Barandella and colleagues argued that the Planck collaboration's filters and calibration made its analysis insufficiently sensitive to the particular dipole they had measured. The Planck result, in their view, therefore did not directly invalidate the original detection. critics responded that if a phenomenon depends strongly on a particular filtering procedure and does not appear robustly under other reasonable analyses, that itself is a reason for caution. This disagreement has never acquired the satisfying conclusion that a documentary editor might prefer. There was no meeting at which everyone shook hands and agreed that dark flow either definitely existed or definitely did not. The scientific community instead moved toward a more cautious position. The specific claim of an approximately 1,000 km per second coherent flow extending over gigaparsec scales is not considered an established observational fact. Planck's null result remains an important piece of evidence against that strong interpretation. At the same time, the broader subject of large-scale bulk motions has not gone away, and that distinction is essential. Dark flow is one particular claim. Bulk flow is a general phenomenon. Galaxies absolutely do have peculiar velocities. Groups of galaxies absolutely do share coherent motions. The local group absolutely moves relative to the cosmic microwave background. The debate is about how large these coherent flows remain when we examine progressively larger volumes. According to the standard lambda CDM model, the expected bulk flow amplitude should decrease as the measurement volume grows. On scales of a few hundred megaparsecs, the Planck collaboration noted that expected coherent velocities should be only around tens to perhaps 100 km per second, even though individual clusters can have larger, peculiar velocities. Researchers can test that prediction without using Kashlinsky's exact KSZ method. One approach is to estimate distances to large numbers of galaxies independently of their redshifts. Once the true distance is estimated, astronomers can calculate the recession speed expected from cosmic expansion. The difference between that and the observed redshift gives an estimate of peculiar velocity. This is difficult because galaxy distances are notoriously annoying to measure accurately. A small error in distance can become a large error in inferred velocity. Yet modern surveys now contain enough galaxies that statistical bulk flows can be studied on increasingly large scales. This has produced another layer of controversy. Some surveys find flows broadly consistent with lambda CDM. Others find unexpectedly large velocities. A particularly interesting example comes from the Cosmic Flows 4 catalogue. Cosmic Flows 4 contains distance and velocity information for tens of thousands of galaxies and galaxy groups. In 2023, Richard Watkins and colleagues used it to estimate bulk motion in volumes reaching roughly 150 to 200 H-inverse megaparsecs. Their estimated velocities were above 380 km per second, larger than the values they expected under their implementation of the standard cosmological model. The authors reported significant statistical tension with lambda CDM, especially for the larger volume. At first glance, that sounds like dark flow returning. It is not. The scales are much smaller than the several hundred megaparsec to gigaparsec ranges involved in the original Kashlinsky claim. The method is different. The measured velocities are also lower than the approximately 1,000 km per second dark flow originally proposed. Most importantly, other researchers analysing the same general data problem have found that the significance depends strongly on how survey geometry, estimator bias, and uncertainties are handled. A separate 2023 study by Amy Whitford, Chris Howlett, and Tamara Davis tested several bulk flow estimators using mock surveys. They found that uncertainties can be underestimated and that survey geometry can strongly affect precision. Using one estimator on Cosmic Flows 4, they obtained a bulk flow of about 408 plus or minus 165 km per second at a relatively shallow effective depth, which they described as reasonably consistent with lambda CDM. Using another estimator reaching deeper, they found about 428 plus or minus 108 km per second, which was in tension with the model. Same catalogue, different estimator, different level of disagreement with cosmology. If you are beginning to suspect that measuring cosmic motion is difficult, you have understood the main point. Another reconstruction of cosmic flows 4 examined velocities out to around 300 H-inverse megaparsecs. That study found some excess bulk motion, especially in one component roughly toward the Shapley concentration, but characterized the overall discrepancy with lambda CDM as around 2 to 3 standard deviations, and said it was somewhat unusual rather than compelling evidence against the model. These newer measurements are interesting because they show that the general question of cosmic bulk motion remains active. A 2026 review of large-scale peculiar velocities describes bulk flows themselves as well established, while noting continued disagreement over their amplitude and how rapidly they decline with scale. It treats the extreme dark flow reports as a particularly dramatic and still contentious part of the broader discussion, rather than as a confirmed feature of the universe. That is probably the most useful way to think about the situation today. There are 3 separate questions. The first is whether galaxies have coherent large-scale motions. Yes, there is no serious controversy about that. The second is whether some observed bulk flows are larger than the simplest lambda CDM expectations. Possibly. Different surveys and analysis methods continue to produce somewhat different answers, especially on scales of a few hundred megaparsecs. The third is whether hundreds of galaxy clusters across billions of light years share an approximately 1,000 km per second motion, requiring an explanation beyond ordinary observable structure. That is the dark flow claim, and that claim remains unconfirmed. The distinction matters because it is very easy to find a modern paper reporting an unexpectedly large bulk flow and announce that dark flow has been proven after all. That would be misleading. Suppose researchers find that galaxies within a sphere about 600 million light-years across have a common velocity of 400 km per second. That could be important. It could indicate unusually strong local structure. It could reveal biases in distance measurements. It might even create some tension with the standard model, but it does not automatically demonstrate a 1,000 km per second flow continuing for several billion light years. Scale changes the question. A local current can be produced by local geography. A current spanning an ocean requires something else. There is another reason the controversy has proved difficult to settle completely. The kinetic Sunyaev-Zeldovich effect is real. Astronomers have detected it statistically using several techniques. Modern experiments have used correlations between microwave maps and galaxy surveys to measure the motion of ionized gas. So the underlying physics used by the dark flow team is not imaginary. The disagreement concerns whether that effect was successfully converted into evidence for one enormous coherent bulk velocity. New CMB experiments should continue improving these measurements. Higher angular resolution allows researchers to separate cluster signals more effectively. Better frequency coverage helps remove foregrounds. Larger cluster catalogues increase statistical power. Spectroscopic galaxy surveys provide more precise redshifts and better maps of the structures around clusters. Eventually, bulk velocities may be reconstructed using combinations of observations that are much less sensitive to the particular filtering arguments that dominated the original dispute. That is how controversial results often become useful, even when they are not confirmed. They expose the weak points in existing methods. Before dark flow, the kinetic Sunyaev-Zeldovich effect was already interesting. After dark flow, there was much greater motivation to understand exactly how well it could be used to measure coherent cluster velocities. Researchers had to think carefully about CMB covariance. They had to test filters. They had to improve cluster catalogues. They had to compare WMAP and Planck. They had to develop statistical techniques capable of separating very small signals from the primordial microwave background. Even if the original interpretation eventually disappears completely, the argument helped push the measurement problem forward. There is also something useful about the way the controversy demonstrates how scientific language changes as evidence changes. In 2008 and 2010, NASA material describing the work used direct language about a newly detected dark flow, while also noting that its interpretation was uncertain. After Planck, the wording became much more cautious across the wider community. The phenomenon was increasingly described as a claim, a proposed flow, a disputed detection. That is not scientists covering up an inconvenient result. It is exactly what should happen when independent tests weaken confidence. Scientific knowledge is not a collection of permanent announcements. It is a ranking of explanations according to the strength of the evidence available at a particular time. Sometimes the ranking changes. Dark flow sits in an awkward middle position because its original advocates continued to find a dipole in later data, while independent analyses did not establish the enormous coherent velocity implied by their interpretation. So is dark flow real? The careful answer is that the specific giant flow described in the original papers has not been convincingly established. There is no broad scientific consensus that something beyond the observable universe is pulling galaxy clusters together. Planck provided strong evidence against a bulk flow of the originally proposed scale using its own analysis. Independent WMAP analyses also questioned the significance. More recent peculiar velocity surveys show that the broader issue of unexpectedly large motions is still interesting, but those measurements are not direct confirmation of the original dark flow. That may sound less exciting than simply declaring that an invisible structure beyond our horizon is dragging galaxies through space. It is also more interesting in another way. We are left with a real scientific fork. Suppose future measurements continue improving, and the strongest dark flow signal never returns. Then the episode becomes a lesson in how difficult it is to extract tiny velocity information from the microwave sky. But suppose improved surveys eventually reveal a large coherent motion that cannot be accounted for by known structures or ordinary statistical fluctuations. Then the old question comes back immediately, and this time with much stronger evidence behind it. Where did that motion come from? A confirmed primordial bulk flow would not simply add another unusual object to the catalogue of astronomy. It could tell us something about the initial conditions of our observable region. It could constrain how inflation began and how long it lasted. It might reveal that the patch of space that became our observable universe was not perfectly isolated from much larger structures before inflation separated them. It could even give cosmologists a way to test ideas about what happened earlier than the oldest light we can observe directly. Those possibilities are the reason dark flow remains worth discussing, even with a large question mark attached to it. The value of the idea is not only in whether the original measurement survives, it forces us to ask what a genuine motion of that size would mean, and that takes the discussion away from the details of microwave filters for a while, and back toward the very beginning of the universe, when the matter now spread across billions of light years, occupied a far smaller region, and when a large-scale push, if one ever existed, would have had its best chance to leave a trace that could still be moving through the cosmic web today. If a large primordial motion really survived from the earlier stage of cosmic history, it would tell us something very different from the discovery of another supercluster. A supercluster would give astronomers information about where matter collected after galaxies formed. A primordial bulk flow could contain information about conditions that existed before galaxies, before stars, before atoms, and possibly before the period of inflation had finished smoothing the region that eventually became our observable universe. That is why the original dark flow interpretation attracted so much attention despite the difficulty of the measurement. The interesting part was never simply that galaxies might be moving quickly. Galaxies do that all the time. The interesting possibility was that their shared motion might be older than the structures containing them. To see how that could happen, we have to return to the very early universe, when there were no galaxy clusters available to move in any direction. The matter now contained in the Milky Way, Andromeda, the Great Attractor, Shapley, and every distant cluster in the dark flow surveys was once part of an extremely hot, dense early cosmos. As the universe expanded and cooled, that material eventually formed particles, atoms, gas clouds, stars, galaxies, and the cosmic web. But the universe was not perfectly uniform at the beginning of the period we can reconstruct observationally. The cosmic microwave background proves that. Its tiny temperature differences reveal small variations in the density of the early universe. Those variations were only around 1 part in 100,000, but gravity had billions of years to enlarge them. A region containing slightly more matter attracted more material. The overdensity increased. Dark matter collected. Ordinary gas fell into the resulting gravitational wells. Eventually the first stars and galaxies appeared. Later, groups and clusters formed. The complicated universe surrounding us today grew from very small differences in the early distribution of matter. Modern inflationary cosmology provides an explanation for where at least some of those differences may have come from. During inflation, extremely small quantum fluctuations could have been stretched to enormous scales as space expanded rapidly. After inflation ended, those fluctuations remained as differences in density. Much later, they became the seeds of cosmic structure. Planck's measurements of the cosmic microwave background strongly support a primordial fluctuation pattern that is close to the simple form expected from many inflationary models. The final Planck results found the primordial perturbations to be predominantly adiabatic and close to Gaussian, with a slightly tilted spectrum rather than a perfectly scale-invariant one. They also found no convincing evidence for many of the more complicated features that could have appeared in the primordial spectrum. That success is important because inflation was not invented to explain dark flow. Inflation already solves several separate cosmological problems. One of the most famous is the horizon problem. Look in 2 opposite directions in the sky, and you find regions of the cosmic microwave background that have almost exactly the same average temperature. Today, those regions are separated by an enormous distance. In a simple, expanding universe without inflation, there would not have been enough time for them to exchange information and reach nearly identical physical conditions before the microwave background was released. Yet they match extraordinarily well. Inflation changes the geometry of the problem. Before the rapid expansion, regions that are now extremely far apart could have been much closer and capable of interacting. Then inflation stretched them across enormous distances. Their similar conditions are not a coincidence because they once belonged to a much smaller connected region. There is also the flatness problem. Measurements indicate that the large-scale geometry of the observable universe is extremely close to spatially flat. Inflation naturally drives a region toward apparent flatness, in much the same way that a tiny section of Earth's surface appears flat when you examine only a small enough area. Planck, particularly when combined with measurements of baryon acoustic oscillations, found the universe to be consistent with spatial flatness to very high precision. Inflation therefore takes a small region and expands it enormously. That raises a question that is directly relevant to dark flow. What was happening outside that small region before inflation expanded it? The standard inflationary picture does not give us a confirmed observational answer. We do not know whether the universe existed for a long period before inflation. We do not know whether inflation began everywhere simultaneously. We do not know whether our observable region was one part of a much larger environment with substantial variations on scales far beyond what we can now see. ESA notes that the earliest fraction of cosmic history remains much more uncertain, observationally, than the later universe, even though the cosmic microwave background gives us indirect information about inflation. This is where a genuine dark flow could become useful. Imagine that the small region destined to become our observable universe was not perfectly balanced before inflation. Perhaps there was a very large concentration of energy or matter beyond one side of that region. Not a galaxy cluster, because galaxies did not exist yet. Not a supercluster. Something much more primordial. Its gravitational field could produce a slight acceleration across our entire patch. Everything in the patch would acquire a common component of motion. Then inflation begins. Space expands by an extraordinary amount. The original region becomes vastly larger. Whatever created the gravitational imbalance may be carried so far away that it ends up beyond our present observable horizon, but the matter inside our region already has the motion. Later, the universe cools, dark matter begins clumping, gas forms galaxies, galaxies form clusters. Each cluster develops its own peculiar velocity because of nearby gravitational structures. Yet underneath those individual motions, a tiny common component could remain from the much earlier acceleration. That is the general kind of fossil a confirmed dark flow might represent. The word fossil is useful here because the proposed motion would not necessarily tell us where the original source is today. A fossil records earlier conditions. It does not require the thing that produced it to remain nearby. Consider the cosmic microwave background itself. The patterns in the CMB are not being created today by the same plasma that existed 13.8 billion years ago. They are a surviving record. Likewise, the chemical abundances of hydrogen and helium preserve information about nuclear reactions in the young universe. Large-scale galaxy distributions preserve information about primordial density fluctuations. Cosmology works largely by studying leftovers. The universe does not provide recordings of its childhood. It provides consequences. A primordial bulk velocity could be another consequence. If astronomers measured it precisely, they could ask how strong the original gravitational gradient must have been. They could estimate the scale of the fluctuation that produced it. Then they could compare those numbers with models of inflation. That comparison could potentially tell them something about how long inflation lasted. The duration of inflation is often described using something called the number of e-folds. One e-fold means the scale of the universe increases by a factor of approximately 2.718. After another e-fold, it increases by that factor again. This becomes enormous very quickly. After 60 e-folds, a scale is increased by roughly 10 to the 26th power. Inflation does not need very much time in an ordinary human sense to produce an extraordinary change in scale. The exact number of e-folds relevant to our observable universe depends on the inflationary model and on what happened afterward. But the general principle is simple. More inflation means that pre-existing irregularities are stretched farther away. If inflation continued for significantly longer than the minimum necessary to produce our observable region, traces of whatever existed before it could be pushed to scales far beyond anything we can measure. Our visible patch would look extremely uniform. A measurable pre-inflationary bulk flow would therefore raise an interesting possibility. Perhaps inflation lasted only somewhat longer than the amount needed to generate the observable universe we see. In that case, some features from the pre-inflationary environment might remain close enough in scale to affect observations. That would be an extremely important constraint. Instead of merely concluding that inflation occurred, researchers might begin learning something about its duration and initial conditions. At the moment, observations do not provide that conclusion. Planck's measurements actually show how successful a remarkably simple inflationary picture can be. Its final cosmological analysis found no evidence for departures from a basic power law primordial spectrum in the ways many exotic models would produce. A strong dark flow would change that discussion because it would introduce a preferred direction. That word preferred matters. The standard cosmological model assumes that the universe is statistically isotropic on sufficiently large scales. There should not be one fundamentally special direction. Locally, of course, directions are different. Look toward the center of the Milky Way, and you see something very different from what you see toward an empty patch of intergalactic space. Look toward the Great Attractor, and the distribution of nearby matter differs from the opposite side of the sky. But those are local structures. Average over sufficiently enormous distances, and no direction should possess a special physical status. A primordial flow across billions of light years would challenge that expectation. It would mean that our observable region contained a large-scale directional memory. Matter would have inherited a velocity favoring one axis. That does not necessarily destroy inflation. There are inflationary models capable of producing unusual large-scale features. But it would mean the simplest version of the story was incomplete. Researchers would then look for other signs of the same preferred direction. One obvious place would be the cosmic microwave background. If the early universe possessed a large gravitational gradient, perhaps it affected the CMB as well. Cosmologists have already studied several unusual large-scale features in the microwave sky. There have been discussions of hemispherical power asymmetry, alignments among low-order multipoles, and other large-angle anomalies. Some of these features have memorable names. The so-called cold spot has attracted particular attention. Another set of alignments has occasionally been given the unfortunate nickname Axis of Evil, proving that even cosmologists eventually become bored with neutral terminology. These anomalies are real features of particular statistical analyses of CMB maps, but their physical meaning remains uncertain. Some may be chance fluctuations, some may be affected by foreground removal, some may reflect the difficulty of performing statistics when we have only one observable universe. Planck's final analysis found that the standard statistically isotropic lambda CDM model still gives an excellent overall description of the CMB, even though some large-scale anomalies remained interesting enough to study. A confirmed dark flow aligned with another independent primordial anomaly would therefore receive much more attention than either signal alone. Imagine that galaxy clusters showed a large coherent velocity in one direction. Now, imagine that the CMB showed an independent large-scale feature along approximately the same axis. Then perhaps polarization measurements or galaxy surveys revealed another related asymmetry. At some point, coincidence would become increasingly difficult to defend. Researchers could begin asking whether all of those observations came from one primordial cause. That is how evidence for new cosmology would probably develop, not from one dramatic measurement, from several different observations converging on the same explanation. A dark flow velocity by itself would not reveal what existed before inflation. It would provide a clue. Other measurements would have to determine what kind of clue it was. There is another possibility. Instead of being caused by a concentration of matter beyond our early patch, a primordial flow might reflect unusual initial conditions in the gravitational field itself. General relativity describes gravity as the geometry of space-time. A very long wavelength perturbation in that geometry could extend far beyond the observable universe. We might occupy only a small section of it. From inside our visible region, we would not see the full structure. We might only experience a gradient. Think about a wave in the ocean with a wavelength of several kilometers. If you stand in a tiny boat and observe only a few meters of water, you cannot see the whole wave. For a while, the surface around you may simply appear to have a slight slope. A cosmological perturbation with a wavelength vastly greater than our observable horizon could look somewhat similar mathematically. We would sample only part of the pattern. Such fluctuations are sometimes called super-horizon modes. They are important in early universe theory because inflation naturally produces correlations on scales that later grow beyond the horizon. A sufficiently large mode could, in principle, influence observables across our entire accessible region. There are serious theoretical constraints on how this can happen. A simple large-scale perturbation cannot automatically produce any bulk motion we want, while leaving the rest of cosmology unchanged. The same perturbation may affect the microwave background. It may create temperature anisotropies. It may alter density distributions. It may produce signatures that observations already restrict very strongly. This is why the theoretical interpretation of dark flow has always been more difficult than saying that some invisible mass must exist in the correct direction. Any proposed primordial source has to explain why the velocity is present without producing other effects that should already have been obvious. That is a demanding requirement. A confirmed signal could also teach us something about the size of the entire universe, not its exact size. Dark flow would not allow an astronomer to write down a number and announce where the universe ends, but it could establish that physically relevant structure exists on scales larger than our observable region. Suppose a bulk flow could only be explained by a perturbation with a characteristic size several times greater than the observable universe. That would provide a lower bound on the scale over which the cosmos contains meaningful connected structure. It would show that our observable patch is embedded in something larger in a measurable way. At the moment, we infer that there is probably more universe beyond our horizon, largely from the success of cosmological models and the absence of any reason for the universe to terminate exactly where our observations stop. A genuine super-horizon influence would be a more direct clue. It would be a little like living on an island surrounded by thick fog. You cannot see another island. Then a long ocean swell arrives from beyond the visible horizon. The swell does not tell you precisely what lies out there. It does tell you that your visible patch of water is not dynamically isolated. Again, the analogy has limits. Cosmic horizons do not behave exactly like fog, and super-horizon perturbations are not ordinary waves arriving from somewhere today. But the observational logic is similar. An effect measured here may contain information about a larger environment. This brings us to one of the more speculative possibilities sometimes associated with early universe cosmology: eternal inflation. In some inflationary models, inflation does not end everywhere at once. It ends in particular regions while continuing elsewhere. Regions where inflation ends can develop into expanding domains, sometimes informally called bubble universes. Our observable universe could lie inside one such region. Other domains might exist beyond any horizon we can cross. Different versions of these models allow different properties in different domains. This is one route by which physicists arrive at the idea of a multiverse. Dark flow has occasionally been linked to such possibilities because a large unexplained directional influence naturally encourages people to ask whether another region of space-time could have affected ours. But this is several speculative steps beyond the measurement. Even if dark flow were confirmed, it would not immediately demonstrate a neighbouring universe. The first task would be to determine whether an ordinary super-horizon perturbation inside a larger version of our own universe could explain it. Only after simpler possibilities failed would more exotic models become useful. There is an enormous difference between saying, our observable region may be part of a larger universe, and saying, another universe is pulling on our galaxies. The first idea fits naturally into standard cosmology. The second requires a very specific theory of how separate regions formed, whether they interacted, and what observable signatures that interaction should leave. Without those predictions, the idea is difficult to test. This is a recurring problem whenever cosmology approaches its observational boundary. Theory can travel much farther than telescopes. Mathematics allows researchers to explore universes with different geometries, different inflationary histories, different initial conditions, additional fields, extra dimensions, and many other possibilities. The challenge is finding some measurement that tells us which description, if any, belongs to reality. A confirmed dark flow could have been one such measurement. It might have allowed cosmologists to discriminate between models that otherwise produce nearly identical observable universes. Suppose two inflationary theories both predict the microwave background we see, both predict the same amount of dark matter, both produce similar galaxy distributions, but one predicts that pre-inflationary gradients should be completely erased, while the other allows a residual large-scale velocity. Measure that velocity accurately and suddenly, the two models no longer look identical. That is why small anomalies can matter so much. Their importance is not proportional to how large they appear in a telescope. A tiny statistical effect can distinguish between very different histories of the universe. The same reasoning applies to primordial gravitational waves. Inflationary models can produce gravitational waves during the rapid early expansion. Detecting their characteristic imprint in CMB polarization would provide valuable information about the energy scale and physics of inflation. Planck constrained such signals but did not detect primordial tensor modes. Its inflation analysis, especially when combined with bicep/Keck measurements available at the time, place strong upper limits on their amplitude. Dark flow would probe a different part of the problem. Gravitational waves could tell us about the dynamics occurring during inflation. A primordial bulk motion might tell us about large-scale conditions surrounding our patch. before or near the beginning of that inflationary period. Those would be complementary clues, and there are not many possible observations that could claim to contain information from such an early stage. Most of what we see in astronomy is relatively recent. A distant galaxy may show us the universe billions of years ago, but galaxies formed long after the fundamental initial conditions were established. The CMB takes us back much farther. Primordial element abundances take us to the first minutes. Inflationary signatures could potentially reach to a tiny fraction of the first second. Any credible trace of what preceded the ordinary inflationary phase would push the reconstruction farther still. That is the scientific prize hidden inside the dark flow debate. Not an invisible monster beyond the horizon. Information about initial conditions. How uniform was the larger cosmos? Did our observable region begin with a preferred motion? How much inflation occurred? Were there structures on scales much greater than anything visible today? Was our patch unusually placed inside a larger environment? Could any trace of that environment survive after inflation? Those are questions that cannot be answered by simply counting nearby galaxies. They concern the setup from which the observable universe developed. For now, the strongest evidence still favours a remarkably simple large-scale picture. Planck's full mission results found excellent agreement between the cosmic microwave background and the 6-parameter lambda-CDM model, while also placing strong restrictions on more elaborate inflationary features. That makes any genuine primordial flow more difficult to accommodate, not less interesting. If future observations continue finding no extreme coherent motion, the standard picture remains intact. If a robust flow eventually appears, measured by independent techniques rather than one fragile statistical method, cosmologists would have to ask which assumption gave way. Perhaps the matter distribution is more unusual than expected. Perhaps the primordial fluctuation spectrum contains a feature we have not resolved. Perhaps inflation had a more complicated beginning. Perhaps our observable universe inherited a velocity from a larger region. Each option would make different predictions. Those predictions would then be tested against the CMB, galaxy surveys, gravitational lensing, peculiar velocities, and future maps of the kinetics and Yaev-Zeldovich effect. Only after surviving that process would a claim about the birth of the cosmos become more than an interesting possibility. There is still one question behind all of them. If the most provocative interpretation were correct, what could actually exist on the other side of our observational horizon? Not simply whether there is more space there, because most cosmologists already allow that possibility, but what kind of structure could create a directional imprint large enough to survive inside our entire visible region? It could be an ordinary overdensity enlarged to a scale we cannot observe directly. It could be a super-horizon fluctuation left from inflation. It could reflect an uneven pre-inflationary environment. More speculative models allow even stranger possibilities. Sorting those ideas requires separating what gravity can plausibly do from what the dark flow measurement has actually established, because somewhere beyond the familiar catalogue of clusters and superclusters is the much harder question of what, if anything, could be responsible for a pull whose source never appears on our map. That missing source is where the dark flow idea becomes both most interesting and easiest to exaggerate. If the original signal represented a real motion, then whatever produced it would need to influence matter across a region far larger than the Great Attractor, Shapley, or any other familiar concentration of galaxies. Yet there is no confirmed object sitting in the required direction with enough mass to provide that influence. So what might actually be there? The least exotic possibility is simply more structure than we have mapped. Astronomers have learned to be careful about declaring a region of the universe empty simply because a survey does not show much there. The history of the Great Attractor is a good warning. For years, part of the relevant structure was difficult to see because it lay behind the plane of the Milky Way. Infrared, radio, and X-ray observations eventually revealed galaxies and clusters that ordinary optical surveys had missed. The Vela supercluster offered another reminder. A major concentration of galaxies had been partly hidden behind our own galaxy and was recognized only after surveys improved. It is therefore reasonable to ask whether some undiscovered collection of superclusters could still contribute to large-scale motion. The difficulty is scale. A hidden cluster is one thing. A hidden structure capable of producing a coherent flow across billions of light years is something else entirely. The gravitational source would have to be extraordinarily large, or the arrangement of several large structures would have to combine in exactly the right way. And gravity leaves evidence. Even dark matter leaves evidence. A huge concentration of unseen mass would distort the movement of visible galaxies around it. It would bend light through gravitational lensing. It would alter the distribution of clusters and filaments. Depending on its size and distance, it could affect the cosmic microwave background as well. The larger the required gravitational source becomes, the harder it is to hide all of its consequences. That is why the most dramatic dark flow interpretation moved the source outside the observable region, rather than simply placing another supercluster behind the Milky Way. But the phrase, outside the observable universe, needs its usual warning label. It does not mean outside the universe. There could be enormous amounts of perfectly ordinary space beyond our horizon. There could be galaxies there. There could be clusters. There could be filaments and voids following exactly the same laws of physics we observe here. We cannot see those regions because their light has not reached us, or because cosmic expansion prevents particular signals from ever reaching us. That does not make the regions supernatural. It simply makes them inaccessible. Imagine that the observable universe is one large patch cut from an even larger cosmic landscape. Inside our patch, the average distribution of matter is fairly uniform when viewed on enormous scales. Beyond our horizon, however, the larger landscape might not be perfectly balanced. Perhaps there is a huge overdensity in one direction. Perhaps our observable region sits on one side of a fluctuation whose full size is far greater than anything we can see. If that structure affected our region early enough, it might leave a directional motion behind. This idea is closer to what the original dark flow interpretation suggested. NASA's description of Kashlinski's early results explicitly raised the possibility that matter pushed beyond our present observable horizon by inflation could have influenced the motion of the cluster population, potentially preserving information about conditions from before inflation. There is an important timing issue here. A mass beyond our horizon today cannot simply pull on us instantaneously. General relativity does not allow gravity to send new information faster than light. If a large structure somehow appeared outside our causal horizon this morning, galaxies here would not immediately begin falling toward it. The influence would need to have been established earlier, when the relevant regions were causally connected. That brings us back to inflation. Before inflation, the material that eventually became our observable universe may have occupied a much smaller physical region. A large gravitational gradient acting across that region could have given the matter inside it a shared velocity. Inflation could then stretch the region enormously. The source of the gradient might end up far outside our present horizon. The velocity, or some statistical trace of it, might remain. If that happened, we would not really be getting pulled by a hidden object today. We would be carrying a very old motion. That distinction is less dramatic than the usual headline, but scientifically it is much more interesting. It means the motion would function as evidence about the initial conditions of our cosmic neighborhood. Suppose you discover a group of stones sliding slowly across a frozen lake in the same direction. You look around and find no current force large enough to explain the movement. One possibility is that something is still pushing them from somewhere you cannot see. Another is that they were given momentum earlier and are continuing to move. Dark flow, in its primordial interpretation, is closer to the second situation. Of course, galaxy clusters do not simply coast freely. They interact gravitationally with surrounding structure throughout cosmic history. Their individual velocities change. Any ancient shared component would have to survive all of those later influences strongly enough to remain measurable today. That places strict conditions on whatever early process produced it. One possible source would be an enormous superhorizon perturbation. A perturbation is simply a variation in density, gravitational potential, or another physical quantity. Superhorizon means the spatial scale of that variation is larger than the region from which information can currently reach us. Imagine a wave so long that you can observe only a tiny fraction of one slope. You would not see a complete crest and trough. You would simply notice that one side of your observable region seems slightly different from the other. A sufficiently long wavelength cosmological perturbation could produce something similar. Our entire visible universe might occupy only a small portion of a much larger variation. From inside, that variation could look like a broad directional gradient. If it influenced matter before the structures we see today formed, that gradient might contribute to a coherent motion. The attraction of this idea is that it does not require another type of universe. It requires only a universe larger than the one we can observe. That is already compatible with many inflationary models. The challenge is making such a perturbation strong enough to produce the claimed flow without creating other effects that observations would have noticed. The cosmic microwave background is particularly restrictive. A large primordial gravitational gradient should generally leave some imprint on the temperature or polarization of the CMB. Planck measured those quantities with extraordinary precision. Its results are broadly consistent with the standard lambda-CDM cosmological model, and with primordial fluctuations that are close to statistically isotropic and Gaussian, although several large-angle anomalies remain subjects of discussion. That means theorists cannot freely add an enormous superhorizon disturbance. They have to make sure it does not ruin the parts of cosmology that already work extremely well. This is a recurring frustration in theoretical physics. An idea may solve one mystery very nicely, and then create 6 new ones before lunch. Suppose a model produces the right dark flow velocity. Good. Does it preserve the observed CMB temperature spectrum? Does it reproduce the galaxy distribution? Does it keep the universe nearly spatially flat? Does it avoid producing a huge anisotropy we should already have detected? Does it preserve nucleosynthesis? Does it fit gravitational lensing? If the answer to several of those is no, the model has not explained dark flow. It has merely moved the problem. Another possibility is that the initial state of inflation itself was uneven. Inflation is often described as though the universe smoothly entered a rapid expansion, and everything became simple from that point onward. The actual beginning of inflation is one of the least understood parts of the theory. We do not know exactly what conditions preceded it. We do not know why inflation began in the region that became our observable universe. We do not know whether that region was typical. We do not know whether neighbouring regions had the same density, geometry, or fields. ESA notes that direct observational knowledge of the extremely early universe is limited, with the period before the epochs probed by the CMB remaining highly uncertain. A confirmed dark flow could therefore suggest that our patch entered inflation with a residual directional imbalance. Perhaps the region was moving relative to a larger surrounding environment. Perhaps a gradient existed in the field driving inflation. Perhaps inflation lasted just long enough to stretch most early irregularities away, without completely erasing one extremely large-scale feature. That last possibility is especially interesting because the amount of inflation matters. If inflation lasts much longer than the minimum required, pre-existing features are stretched to scales enormously larger than our observable universe. Any directional information from the earlier state becomes effectively invisible. If inflation lasted only somewhat longer than necessary, however, traces of the initial environment might remain close enough in scale to affect observations. A real primordial bulk flow could then tell cosmologists something about how long inflation lasted. It might even place limits on the size of the region that existed before our visible universe took shape. That would be an extraordinary use for the motion of galaxy clusters. Instead of using galaxies merely to map where matter is now, astronomers would be using them as surviving markers of an event from a tiny fraction of a second after the beginning of the universe. There are more speculative possibilities. One of them involves eternal inflation. In some models, inflation does not end everywhere. it may continue expanding space in some regions while stopping in others. Regions where inflation ends can evolve into large domains with ordinary cosmic expansion. These are sometimes called bubble universes. Our observable universe could be inside one such bubble. Other bubbles might exist elsewhere in the larger inflating space-time. This is one of the ways physicists arrive at multiverse models. If two such regions interacted early enough, the interaction might leave observable traces. Researchers have looked for possible signatures of bubble collisions in the cosmic microwave background, such as unusual circular patterns or directional asymmetries. No generally accepted evidence for another bubble universe has been found. Planck's detailed tests found the CMB largely consistent with the statistical expectations of standard cosmology, and searches for unusual global geometry and topology did not produce a confirmed alternative structure. This means statements claiming that dark flow is evidence of a parallel universe go far beyond what the observations support. Even if dark flow were confirmed tomorrow, the existence of another universe would not automatically follow. Researchers would first test explanations involving ordinary large-scale structure. Then they would consider superhorizon perturbations within the same universe. Then unusual inflationary initial conditions. Only after simpler models failed would interactions with separate inflationary domains become a serious candidate. Another speculative idea mentioned in discussions surrounding dark flow involves modifications to gravity on very large scales. Perhaps general relativity works perfectly on the scales where we have tested it, but behaves differently across distances approaching a significant fraction of the observable universe. Modified gravity is already studied for other cosmological reasons, particularly attempts to explain accelerated expansion without invoking dark energy in its simplest form. Could some altered gravitational behavior create unusual bulk velocities? In principle, particular models could. In practice, modifying gravity is difficult because general relativity has passed a large range of tests. Any new model has to agree with successful predictions involving planetary motion, gravitational lensing, binary systems, gravitational waves, galaxy clustering, the expansion history of the universe, and the CMB. Changing gravity only where you need it and leaving everything else untouched is rarely available as an option. The dark flow team itself discussed possibilities extending beyond conventional gravitational instability, including pre-inflationary structure and, more speculatively, departures from known gravitational physics. There is also a less exotic candidate that can easily be overlooked because it does not sound mysterious enough. We might not understand the large-scale distribution of matter quite as well as we think. The standard lambda CDM model is extremely successful overall, but cosmology is still dealing with several observational tensions. Measurements of the Hubble constant do not all agree perfectly. Different methods of estimating the clustering amplitude of matter have produced some tension, although its significance depends strongly on the surveys being combined. Large-scale peculiar velocities themselves remain an active area of research. A major 2026 review concludes that coherent bulk motions over scales of several hundred megaparsecs are well established, while reported amplitudes and their agreement with lambda CDM continue to vary among surveys and methods. That does not rescue the original dark flow claim. Several hundred megaparsecs is not automatically equivalent to a coherent flow extending across the observable universe, and a few hundred kilometers per second is not the same as the extreme velocity originally inferred by Kashlinski's group. Still, the newer measurements show why cosmologists have not lost interest in peculiar velocities. Motion contains information that galaxy positions alone do not provide. A map shows where matter is. A velocity field shows where gravity is trying to take it. That makes peculiar velocities sensitive to large-scale mass distributions, including dark matter and structures lying beyond the most obvious clusters. Future surveys could improve this dramatically. Large spectroscopic surveys will measure redshifts for millions of galaxies. Distance indicators will continue improving. Supernova samples will grow. Measurements of the kinetic Snyaev-Zeldovich effect will become more precise, as CMB experiments achieve higher resolution and lower noise. Instead of trying to extract one weak cluster dipole from a relatively noisy microwave map, researchers may eventually reconstruct large portions of the cosmic velocity field using several independent techniques. That will make one particular test extremely valuable. Do the different methods agree? Suppose galaxy distance measurements reveal a large flow, then KSZ observations show the same flow, then supernova distances show it, then reconstruction from the surrounding density field fails to explain it. Now the problem becomes much harder to dismiss as a filtering artifact. On the other hand, suppose increasingly precise measurements continue to show that large-scale velocities decline with scale in roughly the way lambda CDM predicts. Then the original dark flow signal becomes part of the history of difficult measurements rather than evidence of an unseen cosmic source. At present, that second interpretation is close to the scientific mainstream. Planck's 2013 cluster analysis found no significant bulk flow at the scale associated with the original claim and set a blind search upper limit of 254 kilometers per second for its sample. The authors concluded that their measurements were consistent with a universe that is largely homogeneous on gigaparsec scales. The original team continued to defend its method, and the broader subject of large peculiar velocities remains active, but there is no accepted observation requiring something beyond the observable universe to pull galaxy clusters toward it. That may seem like the mystery has become smaller. In one sense, it has. We cannot point toward a Centaurus and say with confidence that an invisible structure beyond the horizon is dragging the universe in that direction. We cannot call dark flow proof of a multiverse. We cannot say that scientists have detected something outside the universe. But there is another way to look at the situation. The fact that such a measurement is even possible tells us something remarkable about cosmology. Galaxy clusters billions of light years away contain hot electrons. Ancient microwave photons pass through those electrons. The movement of the cluster changes those photons by a tiny amount. Satellites measure that change. Astronomers combine hundreds or thousands of clusters and try to reconstruct a velocity pattern. From that pattern, they ask whether matter we cannot see might exist beyond the region we can observe. The chain of reasoning extends from individual electrons to the possible structure of the entire cosmos. Even when the final answer is uncertain, the method itself is extraordinary. There is also no requirement that the most interesting result be the exotic one. Suppose future observations finally demonstrate that there is no dark flow at all. Then the large-scale universe behaves approximately as the standard model predicts. The peculiar motions of galaxies are generated mostly by the cosmic web we can map. The Great Attractor, Shapley, voids, filaments, and dark matter together explain the currents around us. Our observable region has no measurable inherited drift from a larger pre-inflationary landscape. That would still tell us something about the early universe. It would place limits on how uneven conditions could have been outside our primordial patch. It would restrict models that predict large superhorizon gradients. It would strengthen the case that inflation erased most information about whatever came before. A non-detection can therefore constrain the universe almost as usefully as a detection. If the opposite happens and a robust dark flow emerges, then the consequences become much larger. The velocity would need to be measured independently. Its direction would need to be established. Its variation with distance would need to be mapped. Researchers would compare it with the distribution of galaxies and dark matter. They would test whether Shapley, Vela, or more distant structures account for part of it. They would search the CMB for related directional signatures. They would examine whether a superhorizon perturbation could produce the effect without violating other observations. Only after those steps would serious discussion turn toward pre-inflationary structure or a larger cosmological landscape. That is a slower process than announcing that something beyond the universe is pulling us. It is also how an extraordinary possibility becomes science rather than a headline. For now, the safest picture is that the Milky Way is moving through a complicated gravitational environment, just as every other galaxy is. Our local group responds to nearby galaxies, larger clusters, distant concentrations and underdense regions. On larger scales, those motions should become progressively less coherent. Whether some residual current remains stronger than expected is still being measured. What we do not currently have is convincing evidence that the entire observable universe is being dragged toward a hidden destination. And there may not even be a destination. A primordial bulk flow, if one exists, could simply represent inherited motion rather than movement toward a particular object. The arrow on the map would tell us how matter is moving, not necessarily where it will eventually arrive. That is a useful correction because the word flow encourages us to imagine a river. A river has banks, it has a downstream direction. Eventually it reaches somewhere else. Cosmic bulk motion does not need to behave that way. Space is expanding while structures move within it. Gravity changes those velocities. Dark energy changes the long-term expansion. Some galaxies remain gravitationally bound. Others recede beyond horizons. There is no requirement for every large-scale velocity to end at one enormous attractor. So when we ask what might be pulling us through the dark, the possible answers form a wide range. Known superclusters may explain part of our local motion. Unmapped mass could modify the details. Large voids change the gravitational balance. A superhorizon perturbation could, in principle, leave a primordial gradient. Inflationary initial conditions might preserve a larger scale velocity. More speculative theories allow interactions with regions beyond our own inflationary domain or modifications to gravity. And the simplest possibility remains that there is no exceptional pull to explain because the original darkflow signal was not a real bulk motion. At the moment, observations do not allow us to remove that last possibility. They actually give it considerable weight. That leaves the horizon where it has always been, not as a confirmed location of some hidden cosmic object, but as the boundary beyond which our direct observations stop. There may be an enormous amount of universe on the other side. There may be structures far larger than anything visible to us. There may be conditions there that would completely change how we think about our own cosmic neighborhood. But if those regions cannot send us information directly, we have to search for indirect traces inside the part of the universe we can measure. Dark flow was proposed as one of those traces. Whether it survives future measurements or eventually disappears, it has already forced astronomers to sharpen a question that is much larger than the original cluster survey. How can we learn about something that lies beyond everything we can see? For now, the answer is to keep measuring what is moving inside the horizon, because if the larger universe has ever influenced our observable patch, the evidence would have to be somewhere here with us.